Hello there, and welcome to Umber Dreams Archives. I'm so glad you found your way here tonight. Before we begin, take a moment to get comfortable. Let your body settle into wherever you're resting. There's nowhere else you need to be. Where in the world are you watching from tonight? A quiet bedroom where the day has finally released you. A cozy space where you can let your thoughts slow down. Wherever you are, you're exactly where you need to be. Tonight, we're going to explore a chapter of Earth's story that often gets overshadowed by the dinosaurs. We'll discover the remarkable creatures that ruled our planet for tens of millions of years before the first dinosaur ever drew breath. These were the giants of the Permian and Triassic periods, the hunters and grazers of a world so different from ours it might as well be an alien planet. We'll meet sail-backed predators, massive amphibians, and the distant ancestors of mammals. It's a journey that spans nearly 150 million years of Earth's deep past. But don't worry, this isn't going to be a catalogue of monsters designed to unsettle you. Instead, we'll move slowly and carefully through this ancient world, taking our time to understand not just what these creatures were, but how they lived, how they fit into their ecosystems, and what they can teach us about the long, patient story of life on Earth. By the end, I think you'll find that these so-called terrible lizards were simply animals trying to survive, no more frightening than the wildlife we share our modern world with. Just separated from us by an almost incomprehensible gulf of time. If you enjoy these calm explorations of Earth's deep history, a like and subscribe really helps reach others seeking the same peaceful way to end their day. And to those already subscribed, thank you for being here, for trusting me with these quiet hours. So settle in, let your shoulders drop away from your ears, take a slow breath in through your nose and let it out even more slowly through your mouth. And let's begin our slow drift back through time, past the age of dinosaurs, to an Earth that was ancient even to them. There's nowhere you need to be right now, nothing you need to do, just listen and let the story unfold. Let's walk together into deep time. Imagine Earth 300 million years ago. Not just different, but fundamentally alien in ways that challenge everything we think we know about our planet. The continents themselves occupied different positions entirely. What we call North America, Europe and Asia were fused together into a massive supercontinent called Pangaea. Africa and South America hugged close on one side. Antarctica, still tropical and lush, anchored the southern reaches. There were no polar ice caps. The climate was hot, humid, and relatively uniform across vast distances. The atmosphere itself was different. Oxygen levels fluctuated dramatically throughout this period, sometimes reaching 35% compared to our modern 21%. This might seem like a small difference, but it fundamentally changed what was possible for life. Higher oxygen content meant that organisms could grow larger without sophisticated respiratory systems. It's part of why we find dragonflies with 2-foot wingspans fossilized in rocks from this era, and millipedes the size of small crocodiles. The plant life would look strange to us as well. There were no flowering plants yet, no grasses covering the ground. Instead, vast swamp forests of giant club mosses and horsetails dominated the lowlands. Tree ferns grew to enormous sizes in drier regions. Early conifers were just beginning to spread. The whole world had a green sameness to it that would seem monotonous to our eyes, accustomed as we are to the spectacular diversity of modern flora. And in this alien landscape, life was doing what it always does, finding every possible way to exploit every available niche. In the waters, fish are diversified into countless forms. On land, amphibians were at the height of their power. Far larger and more varied than the frogs and salamanders we know today. And most importantly for our story, a group of animals called synapsids, the distant ancestors of all mammals, including us, were beginning their long rise to dominance. This was the world before dinosaurs. A world that had already seen life crawl from the oceans, develop lungs and legs, grow to enormous sizes, and begin the long experiments that would eventually lead to us. The dinosaurs, for all their fame, were latecomers to a planet that had already been experimenting with large land animals for 100 million years. What lived in those vast stretches of time? What ruled Earth before the terrible lizards claimed their throne? That's what we're here to discover together, slowly and carefully, one chapter at a time. And it's this very question of what came before that leads us to our next discovery. To understand these ancient rulers, we must first understand time itself, or rather, the vast, almost incomprehensible depths of time in which their story unfolds. The human mind wasn't built to comprehend geological time. We live our lives in decades, maybe a century if we're fortunate. Recorded human history stretches back about 5,000 years. Anatomically modern humans have existed for perhaps 300,000 years. These numbers feel vast to us because they are, measured against a single human lifespan. But the creatures we're exploring tonight lived 300 million years ago. Let's try to wrap our minds around what that means. If each year of Earth's history were a single page in a book, the story of anatomically modern humans would occupy the last 300 pages. Recorded history would be the last 5 pages. Your entire life would be less than a single line of text. The dinosaurs, for all their fame, would occupy about 35,000 pages, from page 186,000 to page 221,000 or so. The creatures we're discussing tonight, the rulers of the Carboniferous, Permian and early Triassic periods, would fill the pages from about 300 million to 230 million years ago, roughly 70 million pages of our imaginary book. This is what geologists call deep time, and it's important to sit with this concept for a moment because it changes how we see these ancient animals. They weren't failures or evolutionary dead ends. They were wildly successful for tens of millions of years. Some lineages of these creatures persisted longer than the entire span from the first dinosaur to the last non-avian dinosaur. They saw continents merge and split. They survived climate shifts that would have devastated modern ecosystems. They adapted, evolved, and thrived across timescales that make human civilization look like an eye blink. Consider the Dimetrodon, one of the most iconic creatures from this era. We'll meet it properly later, but for now, just know that it lived about 280 million years ago. That means Dimetrodon was separated from the first dinosaur by roughly 45 million years. To put that in perspective, you and I are separated from Tyrannosaurus rex by about 66 million years. The Dimetrodon was more distantly removed from T-Rex than we are. When dinosaurs finally appeared, the age of Dimetrodon was already more ancient to them than the dinosaurs are to us. This perspective matters because it helps us understand that what we're exploring isn't some brief, failed experiment in the history of life. These creatures ruled Earth for longer than dinosaurs did. They developed sophisticated hunting strategies, complex social behaviors, and remarkable adaptations. They were not primitive mistakes waiting for dinosaurs to replace them. They were Earth's dominant megafauna for an enormous span of time, and they shaped the world that dinosaurs would eventually inherit. So as we move forward into their world, let go of any sense that these creatures were somehow lesser or more primitive. In their time, under their conditions, they were as magnificent and as perfectly adapted as any animal that has ever lived. They deserve our respect and our wonder, not our dismissal. Which brings us gently to where this story truly begins, not with the Permian giants we often picture, but with an even earlier time, when the very first large land animals were still figuring out how to live away from water. Before the mammal-like reptiles rose to dominance, before the great Permian predators evolved, there was the Carboniferous period, lasting from roughly 360 to 300 million years ago. And in this strange, swampy world, insects grew to sizes that would seem nightmarish to us, though we'll find gentleness even in this apparent horror. Picture a dragonfly with a wingspan of over 2 feet, wider than a hawk, hovering over ancient swamps. This was Meganeura, and it was a marvel of evolutionary engineering made possible by that oxygen-rich atmosphere we mentioned earlier. With more oxygen in the air, Insects could grow larger without developing complex respiratory systems. Their simple network of breathing tubes, which would limit modern insects to small sizes, worked perfectly well at larger scales when the air was richer. These giant insects weren't alone. The forest floor crawled with Arthropleura, millipedes that could reach 8 feet in length and weigh several pounds. Imagine a millipede as long as a tall human, rustling through the leaf litter. But here's where we must pause and reconsider our instinctive revulsion. Arthropleura was almost certainly a gentle herbivore, feeding on decaying plant matter and living a slow, peaceful life among the giant club mosses. It had no venom, no aggressive behaviours we know of. It was simply large because it could be, because the environment allowed it. The forests themselves were unlike anything in our modern world. Giant lycopods, relatives of modern club mosses which now grow only inches tall, towered over 100 feet into the air. Their trunks were straight and unbranched for most of their height, topped with a crown of simple leaves. These weren't true trees as we think of them. They had no wood, their trunks supported by thick, rigid bark filled with soft tissue. When they died and fell, they created vast log jams in the swamps, eventually becoming the coal deposits we mine today. The Carboniferous period literally made the coal that powered the Industrial Revolution, 300 million years of patience compressed into black stone. In this world of giant insects and strange forests, the first tetrapods, the four-legged vertebrates, were diversifying. Early amphibians grew to impressive sizes, some reaching 15 feet or more. They were the apex predators of their time, ambush hunters waiting in murky waters for fish or smaller amphibians to venture too close. But they were still tied to water for reproduction, their eggs soft and vulnerable to drying out. The stage was set for something new. Some of those early tetrapods were beginning to develop different strategies, adaptations that would eventually free them from the water entirely. Their eggs were developing harder shells. Their skin was becoming less permeable, better at holding in moisture. Their lungs were becoming more efficient, their legs stronger and more suited to supporting their weight on land. These small changes, accumulated over millions of years, would lead to the amniotes, the group that includes all reptiles, birds and mammals, and from those early amniotes would come the creatures that truly dominated land before the dinosaurs, the remarkable group we know as synapsids. Let that thought settle as we move forward into the Permian, where these synapsids would rise to heights of diversity and dominance that wouldn't be matched until the dinosaurs themselves appeared, tens of millions of years later. The transition from water to land is one of the most important moments in the history of complex life on Earth, and it happened slowly over tens of millions of years. Through countless small adaptations and dead ends and unexpected successes. To understand the creatures that would eventually rule the Permian, we need to understand where they came from, and that story begins with those early pioneers venturing onto land. Around 370 million years ago, in the late Devonian period, certain lobe-finned fish were spending more and more time in shallow water and on mudflats. These weren't fish trying to evolve legs. They were simply fish trying to survive in environments where lakes and rivers periodically dried up. The ability to breathe air, to use their fins to push across mud to reach another pool of water. These were survival traits that happened to also be pre-adaptations for life on land. Tiktaalik is perhaps the most famous of these transitional forms, discovered in Arctic Canada in rocks about 375 million years old. It had the gills and scales of a fish, but also a neck, a trait unseen in fish. Its fins had the beginnings of wrist bones, allowing it to do something like push-ups on the bottom of shallow streams. It could probably survive out of water for short periods, gulping air with primitive lungs. It wasn't trying to leave the water behind, it was simply well adapted to the shallow, weedy environments where it lived. Over millions of years, some descendants of these fish-like creatures became more committed to land life. Their fins became legs, though still rather sprawling and inefficient compared to later animals. Their vertebrae became stronger to support their weight without water's buoyancy. Their skulls changed shape, Their eyes adapted to seeing in air rather than water. Their hearing evolved to detect airborne sounds. But there was still a major limitation. These early tetrapods, the amphibians, had to return to water to breed. Their eggs lacked waterproof shells. Laid on land, they would simply dry out. This meant that even the largest, most terrestrial amphibians were still tied to lakes, rivers, and swamps for at least part of their lives. They could venture onto land to hunt or bask, but they couldn't truly leave the water behind. And this limitation shaped the ecology of the Carboniferous and early Permian. Amphibians could grow very large, some reaching lengths of 15 feet or more, and they were the apex predators of their time. But they were ambush hunters, waiting in or near water for prey to come to them. They couldn't chase prey across dry land for extended periods. They couldn't live in arid environments. They were successful within their constraints, but they were constrained nonetheless. The breakthrough came with the evolution of the amniotic egg, an egg with a waterproof shell and internal membranes that allowed the embryo to develop fully on land. The exact timing is uncertain, but by about 320 million years ago, the first amniotes had appeared. These were small, lizard-like creatures, not impressive to look at, but they carried within them the seed of revolution. They could lay their eggs anywhere, could live their entire lives on dry land if they chose. From these humble beginnings, two great lineages would emerge. One would lead to all modern reptiles and birds, the sauropsids. The other would lead to mammals, the synapsids. And it's this second lineage, the synapsids, that would produce the true rulers of the Permian period. The creatures we've come here to meet. And this connects to something equally important. The story of how these early synapsids diversified and adapted, eventually giving rise to some of the most remarkable creatures of the pre-dinosaur world. Here's something remarkable that often gets lost in popular accounts of prehistoric life. You're more closely related to Dimetrodon, that sail-backed creature from 280 million years ago, than Dimetrodon was to any dinosaur. Let that sink in for a moment. When we look at the tree of life, the split between synapsids, our lineage, and sauropsids, the reptile lineage, happened very early in amniote evolution. Everything that came after, all the mammals, all the dinosaurs and birds, all the crocodiles and snakes and lizards, they all trace back to that ancient fork in the road. The early synapsids appeared in the late Carboniferous around 320 million years ago. They were small, unremarkable-looking animals, distinguished from early reptiles by seemingly minor skeletal features, particularly the pattern of holes or fenestrae in their skulls behind the eye sockets. Synapsids had one such opening on each side. Reptiles had a different arrangement. This seems like a trivial detail, but that single opening is the beginning of our own story, the first step on a journey that would eventually lead through the Permian giants, to the first mammals, to primates, to you and me. These early synapsids quickly diversified. Some remained small insectivores, probably looking something like stocky lizards, but others began to grow larger, developing adaptations for different diets and lifestyles. By the early Permian, about 290 million years ago, synapsids had split into several major groups. The pelycosaurs, the most famous of which was Dimetrodon, were large predators and herbivores, some with those distinctive sails on their backs. They dominated the early Permian landscape for millions of years. But the pelycosaurs were just the beginning. By the Middle Permian, a more advanced group of synapsids had evolved, the therapsids. These creatures showed signs of becoming more mammal-like. Their legs were starting to move under their bodies rather than sprawling out to the sides, allowing for more efficient locomotion. Their teeth were becoming differentiated into incisors, canines, and grinding teeth, rather than the uniform peg-like teeth of early reptiles. Some of them may have even had the beginnings of hair, though we can't know for certain from fossils alone. The therapsids diversified explosively in the Middle and Late Permian. There were massive herbivores, some reaching the size of modern oxen. There were specialized diggers and burrowers, and most spectacularly, there were the Gorgonopsids, large predators with saber teeth that hunted the Permian plains and forests. For tens of millions of years, synapsids, not reptiles, were the dominant large land animals on Earth. This dominance came from a combination of factors. Synapsids evolved more efficient postures and gaits, allowing them to move faster and with less energy expenditure than their sprawling reptilian contemporaries. They had more diverse teeth, allowing them to exploit a wider range of food sources. There's even evidence that some of them, particularly the more advanced therapsids, may have been developing higher metabolic rates, moving toward the warm-blooded condition of modern mammals. But perhaps most importantly, they were adaptable. As Pangaea formed and climates changed, as environments shifted from swampy lowlands to drier highlands, synapsids evolved forms suited to each new niche. They survived multiple climate fluctuations, adapted to changing vegetation, and maintained their dominance for roughly 70 million years, a span of time longer than the entire age of dinosaurs. Understanding that these creatures are part of our own lineage changes how we see them. They weren't failures or evolutionary experiments that led nowhere. They were our ancestors' ancestors' ancestors, repeated back through millions of generations. Every synapsid that successfully reproduced, that survived long enough to pass on its genes, is part of the chain that leads directly to us. We carry their legacy in our bones, our teeth, our very metabolism, and so we find ourselves at the threshold of the Permian world at its height, ready to meet some of these remarkable ancestors face to face, beginning with perhaps the most iconic of them all. If you picture _0_ with a great sail on its back, you're actually thinking of Dimetrodon, and it lived 45 million years before the first dinosaur ever appeared. This is one of the great confusions of popular paleontology, but it's an understandable one. Dimetrodon had the size, the teeth, and the predatory lifestyle we associate with great carnivores. It just happened to be our relative rather than a reptile. Dimetrodon lived during the early Permian, from about 295 to about 272 million years ago. It was one of several related genera of sail-backed pelycosaurs, but it was the largest and most successful predator among them. The largest species, Dimetrodon angelensis, could reach 15 feet in length and weigh over 500 pounds. Its sail, the defining feature, could stand 3 feet tall, a dramatic structure of elongated vertebral spines covered in skin. But what was that sail for? This is a question that has intrigued paleontologists for over a century, and the honest answer is that we still don't know for certain. The most common hypothesis is thermoregulation. A large surface area covered in skin and blood vessels could help the animal heat up quickly in the morning sun, or cool down by angling away from the sun, or catching a breeze. Computer models suggest this could have allowed Dimetrodon to reach optimal body temperature hours before its prey, giving it a significant hunting advantage in the cool dawn hours. There are alternative theories, though. The sail might have been a display structure, used in courtship or territorial disputes, much like the frill of a triceratops or the crest of a rooster. Different species of Dimetrodon had differently shaped sails. Some were tall and narrow, others lower and more elongated. This variation might suggest display rather than pure function, or perhaps both purposes were served. What we know more certainly is how Dimetrodon lived. It was an apex predator in the early Permian ecosystems of what is now Texas and Oklahoma. Its skull was large and deep, filled with teeth that were differentiated by function, a very mammal-like trait. It had large canine-like teeth for piercing and holding prey, smaller incisors at the front and shearing teeth further back for cutting meat. This dental arrangement tells us it was a dedicated carnivore, probably hunting large prey rather than snapping up insects. Its posture was still somewhat sprawling, legs extending out to the sides, similar to modern crocodiles, though not as dramatically splayed. It probably wasn't a fast runner, at least not in pursuit. More likely it was an ambush predator or a patient stalker, using cover to get close to prey before a final rush. Its prey would have included large amphibians, smaller pelycosaurs, and other early amniotes. Dimetrodon was successful for over 20 million years, an enormous span. Multiple species evolved and went extinct within the Dimetrodon lineage, each adapting to changing conditions, to new prey animals, to competitors. By the time the last Dimetrodon vanished around 272 million years ago, the world was changing. Climate was shifting. Other synapsids were evolving more efficient body plans, and the pelycosaurs as a group were in decline. But Dimetrodon's legacy lived on in its descendants. The pelycosaurs gave rise to the therapsids, those more advanced mammal-like reptiles we mentioned earlier, and through the therapsids, eventually came the mammals, came us. Every time you see a reconstruction of Dimetrodon, understand that you're looking at a very distant relative, a branch on your own family tree that split off nearly 300 million years ago, but nevertheless connects directly back to you. This connection, this deep family relationship across incomprehensible time, is part of what makes these ancient creatures so compelling. They're not aliens or monsters. They're family, separated from us by millions of generations but linked nonetheless by an unbroken chain of life and reproduction. Building on this foundation, we can now explore the broader world in which Dimetrodon lived, the strange and wonderful Permian ecosystems that have no modern equivalent. The Permian period lasted from about 299 to about 252 million years ago, and it was a time unlike any before or since in Earth's history. The supercontinent Pangaea was fully formed, creating environmental conditions that would be impossible with our current continental configuration. Imagine all of Earth's landmass fused into one massive continent stretching nearly from pole to pole, and you begin to understand the Permian world. The interior of Pangaea was extraordinarily dry. With so much land far from any ocean, the moderating influence of water was absent. Seasonal temperature swings were extreme. Vast deserts dominated the central regions, some of the largest in Earth's history. Seasonal monsoons would bring torrential rains to some areas, followed by long dry periods. It was a land of extremes, and life adapted accordingly. The coastlines and river valleys, where moisture was more reliable, supported lush vegetation. Early conifers had evolved and were spreading, creating forests quite different from the club moss swamps of the Carboniferous. Tree ferns still grew in wetter areas. Seed ferns, which despite their name weren't true ferns but an extinct group of seed plants, were diverse and abundant. These plants provided food for an array of herbivores and shelter for smaller animals. The animal life was diverse in ways we can barely imagine. This wasn't a world of a few dominant species. This was a world experiencing evolutionary experimentation on a grand scale. In the early Permian, pelycosaurs like Dimetrodon shared the landscape with massive herbivorous pelycosaurs like Edaphosaurus, which had its own distinctive sail, possibly for similar thermoregulatory purposes. Large amphibians still lurked in the waterways. Early reptiles scurried through underbrush. By the middle and late Permian, the therapsids had taken over. These more advanced synapsids came in a bewildering variety. There were the dinocephalians, bizarre creatures with thick skulls that they may have used in headbutting contests. Some were herbivores, others carnivores, and they ranged from dog-sized to larger than a modern grizzly bear. Their reign was relatively brief in geological terms, perhaps 10 million years, but during that time they were the dominant megafauna. Following the dinocephalians came other groups. The Dicinodonts evolved to become the most successful herbivores of the late Permian and early Triassic. They had a distinctive pair of tusks and a horny beak, and they ranged in size from rat-like creatures to elephant-sized browsers. They filled ecological roles similar to modern ungulates, grazing and browsing across Pangaea's varied landscapes. And then there were the predators, the Gorgonopsids, and their relatives. These were the apex predators of the late Permian, and we'll meet them properly in our next chapter. They stalked the Dicinodonts and other herbivores through forests and across open plains, their saber teeth glinting in the Permian sun. What's remarkable about the Permian world is its completeness, its ecological sophistication. This wasn't a primitive world waiting for better animals to evolve. This was a fully realized biosphere with complex food webs, migratory patterns, seasonal behaviors, all the intricate interactions we see in modern ecosystems. The animals had adapted to their environments over tens of millions of years. They were as perfectly suited to their world as modern animals are to theirs. The plant life, while less diverse than modern flora, still provided all the necessary ecological foundations. Primary production captured the sun's energy. Herbivores converted plant matter into animal protein. Carnivores regulated herbivore populations. Scavengers and decomposers recycled nutrients. It all worked, beautifully and efficiently for millions of years. Climate varied, of course, as it always has. Ice ages came and went at Pangaea's southern reaches. Sea levels rose and fell. But life adapted and persisted. The Permian world wasn't fragile or primitive. It was robust and resilient, at least until the catastrophe that ended it. But we're not there yet. For now, let's appreciate the Permian at its height, a world of strange and wonderful creatures living out their lives under the same sun that shines on us today, connected to us through time and evolution. Let that thought settle as we move forward to meet the most dramatic predators of this lost world, creatures whose very name means, quote, one after the mythical monsters that could turn men to stone. If you encountered a Gorgonopsid in its prime, in the late Permian forests of what is now Russia or South Africa, you might think you were looking at some kind of massive saber-toothed cat. The resemblance would be striking. A powerful predator with enormous canine teeth, a muscular build, and eyes focused forward for binocular vision. But this would be a case of convergent evolution, of life solving the same problem in similar ways separated by 250 million years. The Gorgonopsids evolved saber teeth long before the first mammal, let alone the first saber-toothed cat. Gorgonopsids appeared in the Middle Permian and reached their peak diversity in the late Permian from about 260 to 252 million years ago. They were part of the Therapsid radiation, more advanced than the Pelycosaurs. Moving toward the mammalian condition, but still very much their own unique thing. Their name comes from the Gorgons of Greek mythology, the snake-haired monsters, a reference to their fearsome appearance, though as we'll see, fearsome is a very human judgment that these animals wouldn't have recognized. The largest Gorgonopsids, like Inostrancevia, could reach 10 to 12 feet in length and weigh upwards of 300 pounds. They had large skulls, accounting for about a fifth of their total body length, filled with differentiated teeth. The canines, though, were the showstoppers, sometimes over 4 inches long, compressed blades designed for stabbing and slashing. Unlike the conical teeth of earlier predators, these were killing tools, shaped by millions of years of evolution for a specific purpose. But here's where we must pause and consider what these teeth tell us about how Gorgonopsids lived. Saber teeth are actually quite fragile. They can break if they hit bone. This suggests that Gorgonopsids were precise hunters, using their teeth to target soft tissue, probably the throat or belly of prey. They likely hunted the decinodonts, those successful herbivores we mentioned earlier, animals that were often as large as or larger than the Gorgonopsids themselves. The hunting strategy was probably similar to modern big cats: stalk, rush, bite, and hold on while the prey weakened from blood loss. The Gorgonopsids' legs were more erect than those of Pelycosaurs, positioned more underneath the body, allowing for better running ability. They probably weren't pursuit predators. Their build suggests power over sustained speed, but a short burst to close the final distance to prey that they could manage. Their skulls show another interesting feature, the beginnings of differentiated jaw muscles. In early reptiles, jaw muscles were relatively simple. In Gorgonopsids, we see more complex attachment points suggesting stronger, more controlled bite forces. This is another step toward the mammalian condition, where specialized jaw muscles would eventually allow for sophisticated chewing behaviors. Did they have hair? We can't know for certain, as soft tissue rarely fossilizes, but some paleontologists suspect that at least some therapsids, and possibly Gorgonopsids, might have had some kind of proto-fur or hair-like structures. These would have helped with temperature regulation, particularly if Gorgonopsids were developing higher metabolic rates. The evidence is circumstantial at best, but it's a tantalizing possibility. What we do know is that Gorgonopsids were incredibly successful for their time. They spread across Pangaea, with fossils found in modern Russia, South Africa, Tanzania, and even Antarctica, which in the Permian was not ice-covered but part of the southern temperate zone. They diversified into multiple genera and species, some as small as dogs, others as large as lions. For at least 10 million years they were the apex predators of terrestrial ecosystems, and then, at the end of the Permian, they vanished completely. Not a single Gorgonopsid species survived into the Triassic period. The catastrophe that ended the Permian, which we'll discuss later, was particularly hard on these large carnivores. With their prey populations crashing, with ecosystems collapsing, the Gorgonopsids had nowhere to turn. They were too specialized, too dependent on the complex food webs that were unraveling. Within what was probably a very short time geologically speaking, they were gone. But what a run they had. 10 million years of dominance spread across an entire supercontinent, evolving some of the most sophisticated hunting adaptations seen up to that point in Earth's history. They were magnificent in their time, perfectly adapted to their world, as worthy of our wonder as any dinosaur or saber-toothed cat. And this connects to something equally important, the story of what these predators hunted, the equally remarkable herbivores that form the foundation of Permian ecosystems. Every successful predator requires a foundation of herbivores to sustain it, and the Permian period had herbivores in abundance, ranging from small to enormous, from rare to incredibly common. These plant-eaters don't get the attention that predators do, but they were at least as important to Permian ecosystems, and often more diverse and numerous. The Dicynodonts, which we've mentioned several times already, deserve particular attention. The name means two dog teeth, referring to the pair of tusks that most species possessed, jutting down from the upper jaw. Combined with a horny beak and powerful jaw muscles, these tusks made Dicynodonts well equipped for digging up roots and tubers, stripping bark from trees, or grazing on tough vegetation. They first appeared in the Middle Permian and quickly diversified into an enormous array of forms. Some Dicynodonts, like Dimetrodon, were small, burrowing creatures, perhaps living in colonies and digging extensive tunnel systems. Fossils from South Africa show burrows with multiple individuals, suggesting some kind of social behaviour, perhaps sheltering together during dry seasons or retreating underground during the heat of the day. These small Dicynodonts might have been something like the Permian equivalent of prairie dogs, common, colonial, forming the base of many food webs. At the other end of the size spectrum were giants like Lysowicea, which wouldn't appear until the late Triassic, well after the mass extinction, but earlier Permian forms were still impressively large. Endothiodon could reach the size of a modern cow, with a barrel-shaped body, sturdy legs, and that characteristic beaked face. These large Dicynodonts were probably the primary herbivores in many ecosystems, filling the role that wildebeest or bison fill today. The sheer number of Dicynodont fossils we find from this period tells us how successful they were. In some fossil beds, particularly in Russia and South Africa, Dicynodont remains vastly outnumber all other vertebrates combined. They were the dominant herbivores, and they remained so even after the end Permian mass extinction. Continuing into the Triassic, and only finally disappearing in the late Triassic when dinosaurs began to rise to prominence. But Dicynodonts weren't the only herbivores. In the early and middle Permian, the Praeosaurs were large, heavily built creatures with thick skulls and bodies covered in bony plates and knobs. They looked somewhat like bulky armoured lizards, though they weren't closely related to modern lizards. Some species reached the size of modern cattle, browsing on vegetation in what is now Russia, China and South Africa. Their armour suggests they needed protection from the large predators of their time, perhaps the earlier Gorgonopsids or other therapsid carnivores. There were also smaller herbivores, various early reptiles and smaller therapsids that fed on plants. These creatures are less well known, partly because smaller animals fossilise less readily, but they must have existed in large numbers to support the ecosystem. Think of modern ecosystems. For every large herbivore, there are dozens of smaller rodents, rabbits, and other small mammals feeding on seeds, shoots, and leaves. The Permian would have had its equivalent. What's fascinating is how these herbivores adapted to the changing vegetation. As conifers and seed ferns replaced the club moss forests of the Carboniferous, herbivores had to develop new strategies for processing food. Conifers are less nutritious than many plants, with tough needles and cones that are difficult to digest. Seed ferns offered good nutrition, but required teeth capable of grinding rather than just chopping. We see these dietary adaptations reflected in the fossil record. Changing tooth patterns, shifting jaw mechanics, different skull shapes optimized for different feeding strategies. The relationship between these herbivores and their environment was complex and dynamic. Herds of Dimetrodons might have migrated with seasonal rains following fresh vegetation. Their feeding would have shaped plant communities, preventing any one species from dominating, creating mosaic landscapes of different vegetation types. Their burrows would have aerated soil, their droppings fertilized it. They were ecosystem engineers, shaping the Permian world as much as it shaped them, and these herbivores in turn supported the predators. The energy from the sun, captured by plants, flowed through Dicenodonts and Pariasaurs, and into Gorgonopsids and other carnivores. It was a complete system, balanced over millions of years, as complex and sophisticated as any modern ecosystem. There's a kind of peace in accepting that these vanished animals once lived full, meaningful lives within their ecosystems, that the Permian world worked, that these strange creatures we'll never see were once as alive and real as any animal alive today. And so we come to understand, slowly, that the Permian was not just a prelude to something better. It was its own age, complete in itself, with its own rules and rhythms. While synapsids dominated the land, the amphibians that had ruled the Carboniferous were still very much alive in the Permian, and some of them were absolutely enormous. These weren't the frogs and salamanders we know today. These were apex predators in their own right, masters of the wetlands and waterways that still existed in the drier Permian world. The temnospondyls were the most diverse and successful amphibian group of the Permian and Triassic. They range from small, salamander-like creatures to true monsters. Prionosuchus from the Permian of Brazil may have reached lengths of 30 feet, making it one of the largest amphibians ever to exist. It had a long crocodile-like snout filled with sharp teeth, a body built for ambush hunting in rivers and lakes. Imagine a creature longer than most crocodiles, lurking in Permian waterways, powerful enough to take even large terrestrial animals that came to drink. The skull structure of these large temnospondyls tells us much about their lifestyle. They had eyes positioned on top of their heads, perfect for floating just beneath the water's surface while keeping watch for prey. Their skulls were flat and broad, with sensory pits that might have detected pressure waves from moving prey, much like modern crocodiles. The teeth were numerous and sharp, designed to grip slippery fish and struggling prey. Despite their size and predatory prowess, these creatures still faced the fundamental constraint of their amphibian nature. They had to keep their skin moist, and most species probably still laid eggs in water. This meant they were tied to wetland environments, unable to venture into the drier regions where synapsids were diversifying. But in their preferred habitats, they thrived. Smaller temnospondyls filled different niches. Some were specialist fish-eaters with narrow snouts. Others had broad shovel-shaped heads, suggesting they might have fed on the bottom, perhaps on aquatic invertebrates or carrion. Some were terrestrial for much of their lives, returning to water only to breed. The diversity of forms suggests a diversity of lifestyles, each species finding its own way to make a living in Permian waters. But the temnospondyls weren't the only amphibians of this time. The lepospondyls were a diverse group of smaller amphibians, some of which looked remarkably like modern salamanders or even snakes. Some were aquatic, with reduced limbs and elongated bodies suited for swimming. Others were more terrestrial, though still tied to moist environments. They were the small vertebrates of their ecosystems, feeding on invertebrates, providing food for larger predators. As the Permian progressed and Pangaea's interior became drier, the amphibians faced increasing challenges. The great Carboniferous swamps were mostly gone, replaced by seasonally dry landscapes with scattered wetlands. Amphibians, dependent on moisture, retreated to the remaining waterways, river valleys, and coastal regions. Their diversity and abundance declined on land, though they remained important components of aquatic ecosystems. Interestingly, some temnospondyls adapted to these drier conditions better than others. Some species developed thicker, more waterproof skin. There's evidence that some might have been able to estivate, going into a dormant state during dry seasons buried in mud, much like some modern lungfish and amphibians do. These adaptations allowed them to survive in environments that would have been fatal to their Carboniferous ancestors. The end Permian mass extinction hit amphibians hard, as it did most groups, but temnospondyls proved remarkably resilient. While many lineages went extinct, some survived and even flourished in the early Triassic. The largest temnospondyls of all time actually lived in the Triassic, not the Permian, taking advantage of ecological opportunities left by the extinction of many synapsid groups. They would persist all the way into the Cretaceous period, finally going extinct around 120 million years ago, outlasting most of the creatures we've been discussing by a wide margin. This resilience is worth contemplating. Amphibians are often seen as primitive or limited, and in some ways they are, constrained by their reproductive biology and their need for moisture. But they've been around for over 350 million years, surviving multiple mass extinctions, adapting to changing conditions, finding ways to persist even as flashier groups rose and fell around them. There's a kind of quiet success in that longevity that deserves our respect. As we think about these ancient amphibians lurking in Permian rivers, let's remember that they represent a lineage that predates all amniotes, that was old even when the first synapsids appeared. They link us back to those first pioneers crawling onto land, to the very roots of tetrapod evolution. And perhaps this is what matters most as we transition into the next phase of our story. Understanding that the Permian world was layered, complex, with old lineages coexisting with new ones, with aquatic ecosystems as important as terrestrial ones, with no single group completely dominant everywhere. Every story we've told so far, every creature we've met, was building toward a single catastrophic moment in Earth's history. 252 million years ago, at the boundary between the Permian and Triassic periods, life on Earth came closer to complete annihilation than at any other time we know of. This event, called the Permian-Triassic extinction or sometimes the Great Dying, remains the worst mass extinction event in Earth's history. The numbers are staggering and worth stating clearly, though gently. Approximately 96% of all marine species went extinct. About 70% of terrestrial vertebrate species disappeared. Entire orders and families, lineages that had existed for millions of years, vanished completely in what was, geologically speaking, an instant. The Gorgonopsids, gone. Most dicynodont species, gone. The majority of amphibians, gone. Even insects, which are usually resilient to extinction events, saw significant losses. What could cause such devastation? The evidence points to a combination of factors, all triggered by massive volcanic eruptions in what is now Siberia. These weren't ordinary eruptions. The Siberian traps, as they're called, involved lava flows covering an area larger than Europe, releasing enormous quantities of greenhouse gases into the atmosphere over a period of perhaps 1 or 2 million years. The immediate effects would have been severe. Volcanic ash darkened the skies, acid rain fell, but the longer-term effects were worse. Carbon dioxide and methane levels soared, triggering runaway global warming. Temperatures rose dramatically, perhaps by 10 to 15 degrees Celsius on average. Oceans became warmer and more acidic, depleting oxygen levels in a process called anoxia. On land, the heat would have been intense, particularly in Pangaea's already hot interior. Many areas might have become uninhabitable, too hot and dry for most complex life. Vegetation died back dramatically. We see evidence of a coal gap in the rock record where almost no coal formed for millions of years, suggesting plant life was drastically reduced. The extinction didn't happen overnight. It played out over perhaps 60,000 years, long in human terms but a geological instant. And it happened in pulses, with periods of severe die-off separated by brief recoveries that then failed. This stop-start pattern might have been even more devastating than a single catastrophic event, preventing ecosystems from stabilizing. For the animals we've been discussing, this was the end. The Gorgonopsids, those magnificent predators that had dominated for 10 million years, had evolved no defense against environmental collapse. They were large animals requiring lots of food, dependent on complex food webs. When herbivore populations crashed, the predators quickly followed. The Dinosaurs, the large armoured herbivores, vanished entirely. Most dicynodont species died out, though a handful of lineages survived. The large temnospondyl amphibians, already stressed by Pangaea's drying climate, found their wetland refuges becoming death traps as temperatures soared and waters became stagnant and oxygen poor. The smaller, more adaptable species had a better chance, but even among them, losses were severe. In the aftermath, Earth was a wasteland. The early Triassic, the period immediately following the extinction, shows signs of devastated ecosystems struggling to recover. Coal gaps, reef gaps. Long periods where normal ecological processes seem to have been disrupted or absent. It took millions of years for biodiversity to rebuild, for complex food webs to re-establish themselves. But here's the critical thing to understand. This isn't a story about failure. The Permian animals, the synapsids and amphibians and early reptiles, had been wildly successful for tens of millions of years. They evolved, adapted, filled every available niche, created complex and stable ecosystems. That an unprecedented catastrophe destroyed them doesn't diminish that success. Nothing could have survived what happened in the end Permian except through luck, being in the right place with the right adaptations at the right time, and some did survive. Small, adaptable dicynodonts made it through, becoming important herbivores in early Triassic ecosystems. Some temnospondyls persisted. Early archosaurs, the group that would eventually give rise to dinosaurs, survived and expanded. And crucially, some small cynodont therapsids, already well on their way to becoming mammals, made it through the catastrophe. From these survivors, all the ecosystems of the Triassic, Jurassic and Cretaceous would eventually arise. The dinosaurs themselves were indirect beneficiaries of the Permian-Triassic extinction, able to expand into ecological roles left vacant by vanished synapsids. But that's getting ahead of our story. For now, let's sit with the weight of this catastrophe, honour the life that was lost, and prepare to see how life, as it always has, found a way to continue, to rebuild, to try again. Which leads us naturally to consider what that recovery looked like, how the survivors began to piece together new ecosystems in a drastically changed world. The early Triassic period, from about 252 to about 247 million years ago, was a time of strange emptiness and gradual recovery. The world that emerged from the Permian-Triassic extinction was fundamentally different from what came before, and it would take millions of years for ecosystems to regain their previous complexity. In the immediate aftermath, the fossil record is sparse. This might partly reflect the difficulty of fossilizing organisms in disrupted environments, but it also suggests that life itself was rare and struggling. The survivors, the small dicynodonts, the early archosaurs, the cynodont therapsids, found themselves in a world with abundant ecological opportunity, but also severe environmental stress. The climate remained hot, possibly the hottest in the Phanerozoic eon, the last 540 million years. The equatorial regions of Pangaea might have been too hot for complex life, creating what some researchers call the Carnian pluvial episode, a time of extreme heat punctuated by intense rainstorms. Life concentrated at higher latitudes, in the northern and southern temperate zones where conditions were more tolerable. One of the most striking features of early Triassic ecosystems is their low diversity. In the Permian, you might find dozens of different vertebrate species in a single area, representing multiple orders and families. In the early Triassic, diversity was much lower. Lystrosaurus, a pig-sized decenodont, makes up over 95% of vertebrate fossils in some early Triassic deposits. It was a world dominated by a few generalist species able to survive in harsh conditions. Lystrosaurus deserves special mention as perhaps the ultimate survivor. It was already widespread in the late Permian, found across Pangaea from modern South Africa to Antarctica to China. When the extinction hit, most species died out, but Lystrosaurus persisted. It was small enough not to require huge amounts of food, adaptable enough to eat a variety of plants, possibly able to burrow to escape extreme heat or cold. In the devastated early Triassic world, these traits were life-saving. For perhaps 1 million years, Lystrosaurus was the dominant land herbivore across much of the world. Fossil beds from this time are sometimes called Lystrosaurus zones, so completely do its remains dominate. This isn't necessarily because Lystrosaurus thrived. Rather, it survived where others couldn't, inheriting a world by default rather than by competitive superiority. But gradually, diversity began to return. New species evolved from survivors, adapting to fill empty niches. The cynodonts, those advanced therapsids that were already quite mammal-like by the late Permian, diversified in the Triassic. Some remained carnivores, medium-sized predators hunting the herbivores. Others became herbivores themselves, developing specialized teeth for processing plant matter. The archosaurs, which had been minor players in Permian ecosystems, began to expand. These reptiles, the ancestors of crocodiles, dinosaurs and birds, proved well suited to the hot Triassic climate. They evolved diverse forms, crocodile-like aquatic predators, small bipedal carnivores, and eventually large terrestrial predators that would compete with and eventually replace the carnivorous therapsids. Plant life also recovered, though more slowly. The coal gap persisted for millions of years, suggesting that forests were sparse. Eventually conifers spread widely, creating the first extensive conifer forests in Earth's history. These forests would have looked somewhat familiar to modern eyes, at least more so than the alien club moss swamps of the Carboniferous. By the Middle Triassic, about 247 to 237 million years ago, ecosystems had regained much of their complexity. Food webs were once again multi-tiered. Large predators hunted large herbivores. Small insectivores abounded. Freshwater ecosystems recovered, with temnospondyle amphibians once again becoming important aquatic predators. This recovery was remarkable, a testament to life's resilience. In less than 5 million years, ecosystems had gone from near collapse to functioning diverse systems. It wasn't a return to Permian conditions, the players were different, the rules had changed. But it was recovery nonetheless, proof that life finds a way even after the worst disasters. Understanding this recovery helps us appreciate the Triassic, not as a transitional period between the Permian and Jurassic, but as its own distinct age with its own remarkable story. The creatures that lived in this reborn world were pioneers in their own right, reconstructing the very idea of a terrestrial ecosystem from whatever pieces remained after catastrophe. And this connects to something equally important, the story of the archosaurs, those reptiles that would eventually dominate the Triassic and Jurassic, giving rise to dinosaurs and ultimately to birds. In the Permian, archosaurs were minor players, small insectivores and carnivores living in the shadows of dominant synapsids. But the Permian-Triassic extinction changed everything, creating opportunities for these adaptable reptiles. By the Middle Triassic, archosaurs were diversifying rapidly, and by the Late Triassic, they would dominate terrestrial ecosystems in a way no group had since the Gorgonopsids. The word "7" means "8", and in the Triassic, they began to earn that name. The group split early into two main lineages. The Pseudosuchians would eventually give rise to modern crocodiles and alligators, though in the Triassic they were far more diverse, including terrestrial predators, armoured herbivores, and even some that walked on two legs. The Avermetatarsalia would lead to pterosaurs, dinosaurs, and ultimately birds. One of the most remarkable things about Triassic archosaurs was their diversity of body plans and lifestyles. Postosuchus, a late Triassic pseudosuchian, was a 20-foot-long apex predator that walked on four legs but could rear up on its hind legs. It had a massive skull filled with serrated teeth. Looking for all the world like a non-dinosaur trying to be a theropod dinosaur, it competed directly with early dinosaurs for top predator roles and was arguably more successful for much of the Triassic. Desmatosuchus was an armoured herbivore, also a pseudosuchian, covered in thick plates and sporting large spikes projecting from its shoulders. It looked like an ankylosaur dinosaur but evolved entirely independently. This is convergent evolution at its finest. Similar environmental pressures leading to similar solutions in unrelated lineages. The early dinosauromorphs, the archosaur group that would eventually include dinosaurs, started small. The earliest known dinosaurs appeared in the Middle Triassic, about 230 million years ago, in what is now Argentina. Eoraptor and Herrerasaurus were dog-sized to wolf-sized carnivores, quick and agile, but not dominant. For tens of millions of years, dinosaurs were minor components of ecosystems dominated by other archosaurs and by therapsids. What advantages did archosaurs have that allowed them to eventually dominate? Several factors seem important. Their more erect posture, with legs positioned directly under the body, allowed for more efficient locomotion and better stamina. Many archosaurs developed more efficient respiratory systems with air sacs extending from their lungs into their bones. Similar to modern birds, this would have allowed higher metabolic rates and better endurance, critical advantages in the hot Triassic climate. Archosaurs also seem to have more effective parenting strategies than many of their competitors. There's evidence that some species guarded nests, that hatchlings stayed with parents for extended periods. This investment in offspring would have increased survival rates compared to the lay-and-leave strategy of many other reptiles. The crocodile line archosaurs, the pseudosuchians, were initially more successful than the dinosaur line. They occupied more ecological niches, had greater diversity, and included the largest land predators of the Middle and Late Triassic. Saurosuchus, from the Late Triassic of Argentina, was 23 feet long, larger than any dinosaur of its time. It was an apex predator that would have had little to fear from the early dinosaurs scurrying around its feet. But at the end of the Triassic, another mass extinction, smaller than the Permian Triassic event but still severe, would reshuffle the deck once more. Many pseudosuchians went extinct in this event, while dinosaurs, for reasons we still don't fully understand, survived and expanded. By the early Jurassic, dinosaurs had become the dominant land vertebrates, a position they would hold for the next 135 million years. For our purposes, what matters is understanding that the Triassic was not simply a waiting room for dinosaurs. It was a time of evolutionary experimentation, with multiple lineages competing for dominance, each trying different strategies. The eventual success of dinosaurs was not inevitable. It was the result of contingency, luck, and whatever traits happened to be advantageous in the specific circumstances of the late Triassic extinction. The archosaurs remind us that evolution doesn't have a direction or a goal. It's simply populations changing over time in response to environmental pressures, with success measured only by survival and reproduction. The Gorgonopsids weren't evolutionary failures. They were successful until they weren't. The Pseudotsuchians weren't evolutionary dead ends. They were dominant until circumstances changed. And dinosaurs, for all their later success, started as underdogs. There's a kind of peace in accepting this randomness, in understanding that there's no grand plan, just life doing what it does, generation after generation, trying and failing and occasionally succeeding. But even as archosaurs rose to prominence, the therapsids, our own ancestors, weren't done yet. They were evolving in remarkable directions, becoming ever more mammal-like. While archosaurs were diversifying and dinosaurs were beginning their rise, the therapsid lineage that had dominated the Permian was still very much alive, evolving in fascinating directions. The cynodonts, a group of advanced therapsids that appeared in the late Permian, survived the extinction and became increasingly mammal-like throughout the Triassic. They are, quite literally, the link between the synapsids we've been discussing and the mammals that would eventually include us. The word cynodont means dog tooth, referring to their differentiated teeth. Unlike the simple, peg-like teeth of early reptiles, cynodonts had distinct incisors for cutting, canines for piercing, and molars for grinding, just like modern mammals. This dental arrangement allowed for more efficient food processing, extracting more energy from each meal, supporting higher metabolic rates. In the early Triassic, cynodonts were diverse and relatively successful. Thrinaxodon, a cat-sized carnivore from South Africa, shows remarkable mammal-like features. Its skull has a secondary palate, a bony shelf separating the nasal passages from the mouth, allowing it to breathe while eating. This seems like a minor detail, but it's crucial for maintaining high metabolic rates. Modern mammals breathe continuously, even while chewing, something early reptiles couldn't do. Thrinaxodon also shows evidence of whiskers. The skull has small pits on the snout where sensory nerves would have emerged, strongly suggesting some kind of sensory hair. If it had whiskers, it probably had body hair too. Hair is one of the defining features of mammals, used for insulation, allowing for endothermy or warm-bloodedness. A hairy cynodont would have been well on its way to being a mammal. The postcranial skeleton of cynodonts also shows mammalian features. Their limbs were positioned directly underneath the body, allowing for an efficient dog-like gait. Their ribs show evidence of a muscular diaphragm, the muscle that powers mammalian breathing, allowing for more efficient respiration than the simple rib pumping of reptiles. These features combined suggest that at least some cynodonts were endothermic, maintaining constant body temperatures through metabolic heat. By the Middle and Late Triassic, cynodonts had diversified into multiple ecological niches. Some remained carnivores, medium-sized predators hunting smaller animals. Others became herbivores, developing complex teeth for processing tough plant matter. Dimetrodon, a sheep-sized herbivorous cynodont from the late Triassic, had elaborate grinding teeth that wore down and were continuously replaced, an adaptation seen in modern herbivores dealing with abrasive vegetation. The smallest cynodonts, creatures like Brazilietherium from the late Triassic of Brazil, were tiny, probably weighing less than a pound. These little creatures were likely nocturnal insectivores, using their whiskers and possibly keen hearing to hunt in the dark. Nocturnal lifestyle would have helped them avoid the large archosaur predators that dominated during the day. It's a strategy that would define early mammals for the next 100 million years, staying small, staying hidden, staying active at night. The transition from cynodont to mammal is gradual and hard to pinpoint exactly. The traditional definition involves changes to the jaw joint. Reptiles have a quadriarticular jaw joint, while mammals have a dentary-squamosal joint using different bones. But this transition didn't happen overnight. Some late Triassic and early Jurassic cynodonts had double jaw joints, using both sets of bones, representing an intermediate state. By the late Triassic and early Jurassic, true mammals had appeared, tiny creatures that would have been difficult to distinguish from the latest cynodonts without careful skeletal examination. These early mammals inherited all the adaptations their cynodont ancestors had developed, fur, high metabolic rates, complex teeth, efficient respiratory systems, possibly even milk production, though soft tissue like mammary glands doesn't fossilize. But for the entire Triassic period, and indeed for most of the Mesozoic era, mammals remained small and relatively inconspicuous. The age of giant mammals would not dawn until after the dinosaurs went extinct. 66 million years ago. For over 150 million years from the late Triassic through the entire age of dinosaurs, mammals stayed small, stayed nocturnal, stayed out of the way, yet they survived. Through multiple climate shifts, through competition with dinosaurs and archosaurs, through the end Triassic extinction and later environmental changes, they persisted. And when the asteroid struck 66 million years ago, ending the reign of non-avian dinosaurs, mammals were positioned to expand into all those newly vacant ecological niches. We are the descendants of those patient little creatures, the cynodonts and early mammals that stayed small and adaptable through the age of giants. Every time you take a breath with your diaphragm, chew food with your differentiated teeth, or shiver to maintain your body temperature, you're using adaptations that evolved in cynodonts 200 million years ago. That continuity across deep time is staggering when you really sit with it. We contain within us the legacy of Permian synapsids, of Triassic cynodonts, of Jurassic mammals hiding from dinosaurs. All that history, all those generations of survival and reproduction, leads directly to you. And perhaps this is what we need to understand as we move forward. The creatures before the dinosaurs weren't failed experiments or evolutionary dead ends. They were our ancestors, the foundations upon which all mammalian life is built. The Triassic period was a time of competition unlike any before or since in Earth's history. Multiple successful lineages were evolving simultaneously, each trying to dominate terrestrial ecosystems. The therapsids, holdovers from the Permian, were becoming increasingly mammal-like. The archosaurs were diversifying explosively. Early dinosaurs were appearing and beginning to expand. All of these groups lived side by side, competed for resources and shaped each other's evolution. In the Middle Triassic, this competition was fairly even. Large carnivorous cynodonts like Cynognathus, which could reach the size of a large dog or small wolf, hunted herbivorous dicynodonts and other prey. At the same time, early archosaurs filled similar predatory niches. There was overlap, competition. But no single group dominated everywhere. Consider the fossil assemblages from the Middle Triassic of Argentina. You find dicynodont herbivores, cynodont carnivores, rhynchosaur herbivores, which were a successful group of archosauromorphs and early dinosauromorphs, all living in the same general area at the same general time. Each group had its own adaptations, its own ecological niche, but there was sufficient overlap that they must have interacted, competed, influenced each other. Rhynchosaurs deserve special mention as one of the forgotten success stories of the Triassic. These reptiles, only distantly related to archosaurs, were extremely abundant in Middle and Late Triassic ecosystems. Some species reached the size of modern pigs, and fossil evidence suggests they sometimes lived in large herds. They had specialized beaks and teeth for processing tough vegetation, particularly seed ferns. In some fossil beds, rhynchosaurs outnumber all other vertebrates combined, suggesting they were the primary herbivores in many ecosystems. But by the late Triassic, the balance was shifting. Archosaurs, particularly dinosaurs, were becoming more diverse and more dominant. The largest land predators were now dinosaurs like Herrerasaurus or pseudosuchians like Saurosuchus, no longer therapsids. Large herbivores were increasingly dinosaurs or armored pseudosuchians, not dicynodonts or rhynchosaurs. What drove this shift? The honest answer is we're not entirely certain. Climate change likely played a role. The late Triassic saw increasing aridity in many regions, with more seasonal variation in rainfall. Perhaps archosaurs, with their more efficient respiratory systems and different water conservation strategies, handled these conditions better than therapsids. There's also the question of reproduction. Dinosaurs and other archosaurs laid hard-shelled eggs, often in carefully constructed nests. Some species showed parental care, guarding nests and possibly feeding hatchlings. This investment in offspring might have led to higher survival rates. Therapsids, becoming increasingly mammal-like, might have been moving toward live birth and extended parental care. Strategies that work well but require significant energy investment from the mother. Another factor might have been sheer luck. Evolution is not deterministic. There's always an element of chance. Perhaps early dinosaurs happened to be in the right place at the right time, survived some localized catastrophe that killed off competing therapsids, and then expanded to fill the newly vacated niches before therapsids could recover. The end-Triassic extinction, about 201 million years ago, seems to have been the final blow for many non-archosaur groups. This extinction, caused by massive volcanic activity associated with the breakup of Pangaea, was less severe than the end Permian event but still significant. Many therapsid lineages went extinct. The Dicinodonts, which had survived the Permian Triassic extinction and even flourished in the early and middle Triassic, finally disappeared. Large rhynchosaurs vanished. Many Pseudosutian lineages died out, but dinosaurs survived this extinction relatively unscathed. By the early Jurassic, they were unquestionably the dominant land vertebrates, a position they would maintain for over 130 million years. The age of mammals wouldn't dawn for another 140 million years after the non-avian dinosaurs themselves went extinct. So the Triassic competition ended with dinosaurs victorious and therapsids reduced to small, nocturnal mammals. But this wasn't inevitable. For most of the Triassic, it wasn't clear which group would ultimately dominate. Multiple outcomes were possible. The fossil record from this time is a testament to evolution's opportunistic nature, to the fact that success is contingent, temporary, and dependent on circumstances beyond any organism's control. Understanding this contingency, this randomness, is crucial. The creatures before dinosaurs, the synapsids of the Permian and the therapsids of the Triassic, were not evolutionary failures. They were successful in their time, well adapted to their conditions, and ultimately subject to environmental changes that favoured different traits. Their story isn't one of failure, but of change, of the constant flux that characterises all of life on Earth. And as we transition into the final acts of our journey, we'll move from specific lineages and competitions to broader themes. How we know, what these ancient creatures can teach us, and why their story, despite ending hundreds of millions of years ago, still resonates with us today. Understanding extinct animals requires more than just studying their bones. We must attempt to reconstruct entire ecosystems, to understand not just what these creatures were, but how they lived, how they interacted, how energy and nutrients flowed through their world. This is paleoecology, and it's a discipline that combines evidence from fossils, geology, chemistry, and modern ecological principles. Let's imagine a day in the late Permian, about 255 million years ago, in what is now South Africa. The sun rises over a landscape that would look alien to us. Scattered conifers and seed ferns, no grass, no flowers. A group of Dicenodonts, each the size of a sheep, emerges from burrows where they sheltered during the cold night. The Permian had seasons. We know this from growth rings in fossil wood, from sediment patterns suggesting periodic rainfall. These Dicenodonts begin to feed, using their beaks and tusks to dig up roots and strip bark from small shrubs. They're social animals. Fossil evidence from burrows shows multiple individuals together. Perhaps this is an extended family group, parents and offspring from multiple generations. Social behaviour provides protection, many eyes watching for predators, cooperative defence if necessary. In the deeper forest, a Gorgonopsid stirs. It's been waiting, patient as only a cold-blooded ambush predator can be. But here we must pause because we don't know if Gorgonopsids were cold-blooded. Some evidence suggests higher metabolic rates in at least some therapsids. If this Gorgonopsid is endothermic, warm-blooded, it would need to feed more regularly, but it would also be more active, capable of sustained pursuit. Either way, it hunts. Perhaps it stalks through the underbrush, using its forward-facing eyes to judge distance, moving slowly until close enough for a final rush. Or perhaps it waits in ambush, erupting from cover when a Dicinodont ventures too close. The hunt succeeds. One Dicinodont is pulled down, those massive canines finding the throat, cutting off air and blood to the brain. The others flee, their social cohesion momentarily broken by panic. The Gorgonopsid feeds, tearing chunks of meat with its specialized teeth. Scavengers, smaller cynodonts and early archosaurs, watch from a distance, waiting for their chance. Nothing is wasted in this ecosystem. The Gorgonopsid will eat its fill and leave. The scavengers will take what remains. Eventually, beetles and other insects will clean the bones. Bacteria and fungi will break down what's left, returning nutrients to the soil. In a nearby river, a large temnospondyle amphibian floats just beneath the surface, eyes and nostrils above water, body hidden below. Fish swim past, unaware. The temnospondyle strikes, massive jaws closing on a fish nearly 2 feet long. It swallows the struggling prey whole, has no teeth suitable for chewing. Its stomach, like a modern crocodile's, can digest scales and bones, extracting every bit of nutrition. This is an ecosystem, a complete system where energy from the sun is captured by plants, transferred to herbivores, and then to carnivores and scavengers. It's recognizable to us because the basic principles of ecology haven't changed. Competition, predation, symbiosis, nutrient cycling. These are universal features of complex ecosystems, whether in the Permian or today. But there are differences too. The plant life is less diverse, less productive in many ways than modern grasslands or forests. This might limit how many herbivores an area can support, which in turn limits carnivore populations. The lower oxygen levels in the late Permian, back down to about 15 to 16% after the highs of the Carboniferous, might have affected endurance in active animals. Climate patterns were different with all continents joined in Pangaea. Seasonal extremes were more pronounced in the interior. Coastal areas had more moderate climates but were subject to intense seasonal monsoons. These climate patterns would have driven animal behavior, migrations following rainfall, seasonal breeding tied to food availability, hibernation or estivation to survive harsh periods. We can infer much of this from the fossils themselves. Bone histology, the microscopic study of bone growth, reveals whether animals grew quickly or slowly, continuously or seasonally. Tooth-wear patterns tell us about diet. The association of fossils, what species are found together, suggests which animals lived in the same places. Trackways show not just that an animal passed through an area, but how it moved, sometimes even revealing behaviour like hunting or herding. There's beauty in this detective work, in piecing together ancient lives from fragmentary evidence. Every fossil tells a story, not just of death, but of life, of an animal that once ate and moved and reproduced, that interacted with its environment, that was part of a functioning ecosystem. These were real places, as real as any modern forest or savanna. The Dicinodonts felt hunger and fullness, fear and safety. The Gorgonopsids experienced the satisfaction of a successful hunt. The temnospondyls basked in the sun's warmth. They were alive in every sense that matters, and their world worked, sustained itself for millions upon millions of years. Let that thought settle as we move forward to consider how we actually know these things, how fossils preserve ancient lives and allow us to read Earth's deep history. The entire story we've been telling is written in stone, in the fossilized remains of creatures dead for hundreds of millions of years. But fossils are not simple, straightforward records. They require interpretation, careful analysis, and understanding of both what can fossilize and what cannot. The discipline of paleontology is as much about understanding the limitations of our evidence as it is about the spectacular finds that make headlines. Fossilization is rare. Most organisms that die are consumed by scavengers, broken down by bacteria, scattered by weather and time. For a fossil to form, burial must happen quickly, protecting remains from scavengers and oxygen. Then minerals must infiltrate the bones or other hard parts, gradually replacing organic material with stone while preserving structure. Finally, geological processes must bring these fossils back to the surface, or near enough that erosion or human excavation can reveal them. Given these requirements, it's remarkable we have any fossils at all, let alone the thousands of specimens that inform our understanding of Permian and Triassic life. Each fossil represents a small miracle of preservation, a tiny window into the deep past. What can we learn from fossils? The bones themselves tell us about size, shape, posture, and locomotion. The skull reveals brain size, sensory capabilities, and dental arrangement. Growth rings in bones, similar to tree rings, show how quickly an animal grew, whether it had seasonal slowdowns in growth, sometimes even estimating age at death. Tooth wear patterns are particularly informative. Herbivore teeth show distinctive wear from grinding plant matter, and the specific pattern can suggest what kinds of plants were eaten. Carnivore teeth show different wear, with fractures and chips suggesting bone consumption. Sometimes we even find stomach contents preserved, direct evidence of the last meal, trackways. Fossilized footprints provide different information. They show how animals moved, whether they walked on 2 legs or 4, how fast they could move. Sometimes trackways preserve evidence of herding behavior, with multiple individuals of the same species walking together. Occasionally we find predator and prey trackways intersecting, suggesting a chase or hunt. A frozen moment of drama from hundreds of millions of years ago. But there's so much fossils can't tell us. Soft tissue rarely preserves. We can infer that Gorgonopsids might have had hair, but we can't know for certain. Colour is almost never preserved. All those vivid dinosaur reconstructions you've seen are artistic guesses, informed but ultimately speculative. Behaviour, particularly complex social behaviour, leaves few traces in stone. This is why paleontologists are so excited when exceptional preservation occurs. The Ediacaran biota, the Burgess shale, the Liaoning fossils from China with preserved feathers and skin impressions. These deposits preserve soft tissue and provide extraordinary insights into ancient life. But such preservation is rare. Most fossils are just bones. For Permian and Triassic animals, our evidence is generally limited to skeletal remains, trackways, and occasional coprolites, fossilized feces that can reveal diet and digestive efficiency. We have tens of thousands of specimens from some species, like the Dicenodont Lystrosaurus, allowing statistical analysis of population structure and growth patterns. For other species, we might have only a handful of specimens, or even just one, making it difficult to distinguish individual variation from species characteristics. Geographic distribution of fossils tells us about ancient continental configurations and animal movements. Finding Lystrosaurus fossils in Antarctica, Africa, India, and China confirms that these now separate landmasses were once connected in Gondwana, part of Pangaea. The similar but distinct fauna of different regions reveals how populations diverged when separated, providing evidence for evolutionary processes. Fossil assemblages, the combinations of species found together, reveal ecological relationships. If we consistently find Gorgonopsid fossils alongside Dicenodont fossils, we can infer they lived in the same places. The Dicenodonts were likely prey for Gorgonopsids. If certain species are only found in deposits representing river systems, we can infer aquatic or semi-aquatic lifestyles. Isotopic analysis of fossil bones and teeth can reveal diet and climate. Different isotopes of carbon and oxygen preserve information about what an animal ate and what temperature it lived in. This chemical fingerprint complements anatomical evidence, sometimes revealing surprising details. The point is that every fossil, every fragment of bone, every trackway adds to our understanding. Paleontology is cumulative. Each new discovery builds on previous work, sometimes confirming hypotheses, sometimes overturning them. Our understanding of Permian and Triassic life has grown enormously in the last 50 years and continues to evolve as new techniques and new fossils come to light. There's a kind of patience required in this work, a willingness to say, we don't know, when evidence is lacking. To update interpretations when new data emerges, to live with uncertainty while still building the best possible picture from available evidence. It's a patience that mirrors the vast timescales we're trying to understand, a recognition that knowledge, like evolution, is a gradual accumulation of small changes over time. And this connects to something equally important, understanding that science isn't about certainty, but about constantly refining our best understanding based on available evidence. When we look at the Carboniferous, Permian, and Triassic periods as a whole, spanning roughly 170 million years, what's most striking is the sheer diversity of forms life tried. This wasn't a progression towards some predetermined goal. This was evolution experimenting, trying every possible variation, with success measured only by survival and reproduction. Consider body size. In the Carboniferous, we had millipedes 8 feet long, dragonflies with 2-foot wingspans. In the Permian, we had Gorgonopsids the size of modern big cats, Dicenodonts ranging from mouse-sized to ox-sized, temnospondyl amphibians 30 feet long. The Triassic gave us even more variety. Tiny cynodonts weighing less than a pound, massive dinosauromorphs and pseudosuchians weighing several tons. Body plan variation was equally dramatic. Four-legged sprawlers like early pelycosaurs coexisted with more erect, four-legged walkers like later therapsids. Some late Triassic archosaurs were bipedal, walking on their hind legs like later dinosaurs. Others were quadrupedal. Some were heavily armoured. Others fast and lightly built. There was no single, 12-way to be a large land animal. Multiple solutions worked simultaneously. Dietary specializations proliferated. Simple insectivores with uniform teeth gave rise to specialized herbivores with grinding teeth. Carnivores with slicing teeth. Omnivores with varied dental batteries. Some herbivores developed beaks, others massive grinding surfaces. Some carnivores had saber teeth for slashing, others had crushing jaws for bone breaking. Still others had numerous small teeth for gripping slippery prey. Reproductive strategies varied. Most reptiles laid eggs and provided no parental care. But evidence suggests some synapsids, particularly advanced cynodonts, might have guarded nests or cared for young. The evolution toward live birth in mammals was happening gradually throughout the Triassic and early Jurassic. These different strategies represent different trade-offs. Many offspring with a little investment versus fewer offspring with high investment. Thermoregulation strategies also diverged. The sale of Dimetrodon might have been for temperature control. Later therapsids seem to have been moving toward endothermy, maintaining body temperature through metabolism. Archosaurs developed different strategies, possibly including something like the heterothermic condition of modern crocodiles, warm when active, cooler when resting. Each strategy has advantages and costs. None is universally superior. What drove this experimental phase? Partly it was opportunity. The Carboniferous through Triassic saw repeated environmental changes, ice ages, warming periods, the formation and breakup of Pangea, fluctuating oxygen and carbon dioxide levels, changing vegetation. Each change created new niches, rewarded different adaptations, allowed new forms to flourish. Extinction events, paradoxically, also drove diversity. By removing dominant forms, extinctions created ecological space for survivors to radiate into. The Permian-Triassic extinction decimated synapsid diversity, but opened opportunities for archosaurs. The end-Triassic extinction reduced pseudo-Suchian diversity, but allowed dinosaurs to expand. From a longer perspective, this entire period was setting the stage for all terrestrial vertebrate life that followed, the basic body plans of all modern land vertebrates. From frogs to birds to mammals were established or prefigured in this time. The transition from water to land, from ectothermy to endothermy, from egg-laying to live birth, from simple teeth to complex dental batteries, all these fundamental transitions were happening. Some experiments failed, at least in the sense that the lineages died out. Gorgonopsids left no descendants. Pliosaurs vanished completely. Most cynodont lineages went extinct, with only one small branch eventually giving rise to mammals. But calling these _13_ misses the point. They succeeded for millions of years, which is all any lineage can hope for. Eventually, environmental changes doomed them, but they'd had their time. Other experiments succeeded spectacularly. The Archosaur body plan was so successful it still dominates land and air, in the form of crocodiles and birds. The synapsid experiments with endothermy, complex teeth, and efficient locomotion eventually led to mammals, now the dominant land vertebrates. These successes weren't predetermined. They resulted from contingency, from being the right form in the right place at the right time. What's beautiful about this is the utter profligacy of evolution, its willingness to try anything and everything, to pursue every possible avenue regardless of how strange the result might seem. Evolution doesn't care about elegance or efficiency except insofar as they aid survival. It doesn't care about long-term viability. It optimizes for immediate reproductive success and lets the future sort itself out. This is why the history of life is so rich, so endlessly fascinating. It's not a story of progress towards some ideal form. It's billions of stories of organisms trying to survive and reproduce in their particular environments, with success measured only in the next generation, and the one after that, and the one after that, for as long as circumstances allow. Understanding this helps us see these ancient creatures not as primitive attempts at modern forms, but as complete in themselves, as successful as they needed to be for as long as they lasted, which in many cases was far longer than humans have existed or likely will exist. Which brings us gently to the question of our own relationship to these ancient creatures, the direct lineage that connects us to the Permian and beyond. Every human being alive today carries within their body the legacy of the Permian and Triassic creatures we've been discussing. This isn't metaphorical or spiritual, it's literal, biological inheritance, passed down through an unbroken chain of reproduction spanning 270 million years. Your teeth, differentiated into incisors, canines and molars, come from synapsids. Early reptiles had uniform peg-like teeth, the development of different tooth types for different functions. Heterodont dentition evolved in pelycosaurs and was refined in therapsids and cynodonts, before being passed down to mammals and eventually to us. Every time you chew food, you're using an adaptation that first appeared in creatures like Dimetrodon. Your breathing, powered by a muscular diaphragm, is a synapsid innovation. Reptiles breathe by moving their ribs, pulling air into their lungs through muscle contractions. Mammals developed a separate sheet of muscle, the diaphragm, allowing for more efficient breathing, for the sustained high oxygen intake needed to support endothermy. This adaptation probably appeared in cynodonts during the Triassic, and has been passed down unchanged through every mammalian generation since. Your hair, your skin covered in insulating fur evolved in therapsids. We have circumstantial evidence suggesting even some advanced pelycosaurs might have had proto-hair. Certainly cynodonts did. Hair provided insulation, allowing for the high, stable body temperatures that characterize mammals. It's an adaptation so fundamental to mammalian life that even whales and dolphins, marine mammals that lost their functional fur, still develop hair follicles during fetal development. Your ears, particularly the 3 tiny bones in your middle ear that transmit sound, come from the jawbones of reptiles. In reptiles, the jaw joint involves the articular and quadrate bones. In mammals, the jaw joint shifted to use the dentary and squamosal bones, freeing the articular and quadrate to become two of the three ear bones, the malleus and incus. This transition happened gradually in cynodonts, with some species having double jaw joints, using both sets of bones. It's one of the most remarkable transformations in vertebrate evolution, and you carry the result in your skull. Your metabolism, your ability to maintain a constant body temperature through internal heat generation, is a therapsid legacy. The evolution of endothermy was gradual, happening over tens of millions of years from the Permian through the Triassic and into the Jurassic. Different therapsid lineages experimented with it, developed it to different degrees. The enodonts that led to mammals were firmly endothermic, and that trait has been maintained in every mammalian lineage since. Even your behaviour might have ancient roots. Modern mammals show extensive parental care, with mothers nourishing young through milk and both parents sometimes protecting and teaching offspring. The evolution of these behaviours is hard to trace in fossils, but some evidence suggests that at least some cynodonts guarded nests and cared for young. The capacity for complex parental behaviour might be part of our therapsid inheritance. All of this means that when you look at a reconstruction of a cynodont, you're looking at a cousin, separated by millions of generations but still family. The gap between you and a Permian Gorgonopsid is wider, the common ancestor more distant, but the relationship still exists. Go back far enough to the early Pelycosaurs 300 million years ago, and you find the ancestors of every mammal that has ever lived or will live. This deep connection is worth contemplating. It means your existence is the result of an unimaginably long chain of successful reproduction. Every single one of your ancestors, going back 270 million years, survived to reproductive age and successfully passed on their genes. The odds of this happening are essentially zero, yet it happened. It had to have happened. Because you exist, it also means you carry within you structures and functions that are hundreds of millions of years old, refined and perfected over countless generations, tested against every environmental challenge that arose in all that time. You are, in a very real sense, a living fossil, a representative of the synapsid lineage that has persisted since the late Carboniferous, that survived the Permian Triassic extinction, that hid in the shadows during the age of dinosaurs, that finally flourished after the end Cretaceous extinction. Understanding this deep ancestry changes how we see ourselves. We're not separate from nature, not special creations distinct from other life. We're part of the same process that created Gorgonopsids and Dicenodonts and Cynodonts, subject to the same evolutionary pressures, carrying the same basic genetic machinery. We're one twig on a vast tree of life that extends back billions of years, connected to every organism that has ever lived through the simple fact of common descent. There's a kind of peace in this understanding, a feeling of belonging to something much larger and older than ourselves, of being part of a story that began long before us and will continue long after we're gone. We're not the pinnacle of evolution, not the goal toward which all previous life was striving. We're just the latest chapter in our particular branch of the family tree, no more or less remarkable than the Gorgonopsids or Cynodonts that came before us. And perhaps this is what matters most, understanding our place in deep time, recognizing our connection to the ancient past, and finding comfort rather than anxiety in our small role in the vast story of life on Earth. We titled this exploration with reference to terrifying creatures, but by now I hope you've begun to question that characterization. What makes a creature terrifying? Size? Teeth? Predatory behavior? If so, modern grizzly bears, sharks, and crocodiles should terrify us constantly. Yet we manage to appreciate them as magnificent animals perfectly adapted to their environments, while also being appropriately cautious around them. The creatures we've been discussing, the Gorgonopsids and massive temnospondyls and sail-backed pelycosaurs, were simply animals trying to survive. They hunted because they were carnivores. Carnivores must hunt to eat. They had large teeth because large teeth are effective tools for capturing and processing prey. They grew large because their environments and food sources allowed it, because larger size brought advantages in competition and survival. The word terrible itself is interesting. In English, it means frightening or very bad, but its root, the Latin terribilis, simply means causing fear or inducing awe. The original sense was closer to awe-inspiring than horrifying. When we call these creatures terrible, we might more accurately be calling them awesome, worthy of our wonder and respect. Consider Dimetrodon. To us, separated by 280 million years and facing no personal danger from it, this creature is simply fascinating. Its sail, whether for thermoregulation or display, represents an elegant solution to biological challenges. Its teeth show sophisticated specialization for a carnivorous diet. Its posture represents a transitional stage in the evolution of more efficient locomotion. There's nothing frightening about this when we view it objectively. The same goes for Gorgonopsids. Yes, they were apex predators with saber teeth, but so is the modern saber-toothed cat, which went extinct only 10,000 years ago and which early humans definitely encountered. We don't consider ancient humans terrifying for having lived alongside saber-toothed cats. We marvel at their ability to survive and thrive despite sharing their world with such predators. The large temnospondyl amphibians, some 30 feet long, might seem monstrous, but modern saltwater crocodiles can exceed 20 feet in length and are formidable predators. We respect them, we're cautious around them, but we also recognize their importance in their ecosystems, their remarkable adaptations, their place in the natural world. The same perspective should apply to Permian amphibians. Part of our fear response to extinct creatures might stem from unfamiliarity. These animals don't fit into our modern categories. They're not quite reptiles, not quite mammals, not quite anything we have experience with. This otherness can be unsettling, but it's also an opportunity for wonder, for appreciating the vast range of forms life has explored, for understanding that our current taxonomic categories are human constructs imposed on a much more fluid and creative natural world. Another source of anxiety might be the mass extinctions we've discussed. The Permian Triassic extinction killed 96% of marine species and 70% of land vertebrate species. That's genuinely catastrophic, and contemplating it can induce existential dread. But here's the thing, life recovered. It always has. 5 major mass extinctions in Earth's history, and life has bounced back from all of them, often to greater diversity than before. The Permian Triassic extinction was the worst, and yet here we are, descended from survivors, living in a world richer in species than the Permian ever was. This isn't to minimize extinction, or suggest we shouldn't worry about the current human-caused extinction crisis. We absolutely should. But it does suggest that life itself is remarkably resilient, that ecosystems can rebuild even after catastrophic damage, that the story doesn't end with destruction, but continues with recovery and renewal. Reframing these ancient creatures from quote 22 to quote 23 changes our relationship with them. Instead of nightmares, they become teachers. They show us what's possible in evolutionary history, how life adapts to changing conditions, how new forms emerge from old ones, how success is temporary but lineages can persist for tens of millions of years if they remain adaptable. They also show us our own deep history, our connection to the vast tree of life, our inheritance of structures and functions that evolved hundreds of millions of years ago. This connection should be a source of wonder, not fear. We carry the Permian and Triassic within us, in our bones and teeth and metabolisms, in the very cells that make up our bodies. So let go of fear. Let go of the idea that these ancient animals were somehow more dangerous or terrible than modern wildlife. Instead, embrace curiosity. Wonder at the diversity of forms life has tried. Marvel at the resilience of ecosystems. Appreciate the vast stretches of time these creatures dominated Earth, and understand that their reign was as legitimate and successful as the age of dinosaurs or the age of mammals. The creatures that ruled before dinosaurs weren't mistakes or monsters. They were Earth's fauna, as natural and appropriate to their time as any animal alive today. They deserve our respect, our fascination, and our wonder, not our fear. And in understanding this, in releasing our anxiety about the deep past, we make room for a more peaceful, contemplative engagement with Earth's history and our place within it. We've journeyed through nearly 150 million years of Earth's history tonight, from the Carboniferous giants through the Permian rulers to the Triassic survivors and the rise of archosaurs. 150 million years is a span so vast that our human minds can barely grasp it. And yet it's only a small fraction of Earth's history and an even smaller fraction of cosmic time. Let's zoom out for a moment and gain some perspective. Earth is about 4.5 billion years old. Life appeared roughly 3.8 billion years ago, simple single-celled organisms in ancient oceans. For billions of years, life remained microscopic, prokaryotes and eventually eukaryotes, evolving slowly in the sea. Complex multicellular life didn't appear until about 600 million years ago in the Ediacaran period. The Cambrian explosion, 540 million years ago, saw the rapid diversification of animal body plans. But these were all marine animals. Land remained barren, lifeless rock and water. Plants colonized land about 470 million years ago. Animals followed, with the first tetrapods appearing about 370 million years ago. The entire story we've been telling tonight, from the Carboniferous to the Triassic, occupies the window from about 360 million to 200 million years ago. 160 million years of deep time. After the Triassic came the age of dinosaurs, the Jurassic and Cretaceous periods, lasting another 165 million years. Then the end Cretaceous extinction 66 million years ago, and the age of mammals began. Humans, anatomically modern humans, have existed for perhaps 300,000 years. Civilization, recorded history, is about 5,000 years old. Put another way, if Earth's history were a 24-hour clock with the planet forming at midnight, life appearing around 4 a.m., the Permian period would occupy about 10 minutes from 9:50 to 10 p.m. The dinosaurs would rule from 10 to 10:40 p.m. All of human history, from the first Homo sapiens to today, would occupy the last 0.2 of a second before midnight. This perspective is simultaneously humbling and liberating. Humbling because it shows how brief and recent our species is, how little of Earth's story involves us. Liberating because it frees us from the burden of centrality, from thinking that we're the point or purpose of 4.5 billion years of planetary evolution. The Gorgonopsids that dominated Permian ecosystems had no awareness of dinosaurs that would come tens of millions of years in their future. The cynodonts evolving toward the mammalian condition had no knowledge that their descendants would eventually become humans. Earth didn't care about these transformations. It simply provided environments, and life adapted to those environments as best it could, generation by generation, without foresight or planning. In the same way, whatever Earth's ecosystems look like 10 million or 100 million years from now, they almost certainly won't include humans, at least not in our current form. Species don't last forever. The average mammalian species persists for about 1 to 2 million years before going extinct or evolving into something sufficiently different to be classified as a new species. Humans have existed for perhaps 300,000 years. We're still relatively young as a species, but our lineage is ancient. The mammalian line extends back through the Cretaceous, through the Jurassic, through the Triassic, back to cynodonts and therapsids and pelycosaurs, and those first synapsids in the late Carboniferous. 320 million years of continuous descent, an unbroken chain of successful reproduction, linking us to those small, lizard-like early amniotes. And even that doesn't go back far enough. Follow the chain further, back through early tetrapods to lobe-finned fish, back through fish to the first chordates, back through the Cambrian explosion to the first multicellular animals, back to single-celled eukaryotes, back to the very first cells that appeared in Earth's ancient oceans nearly 4 billion years ago. You are the descendant of all of that, the inheritor of nearly 4 billion years of evolutionary history, of countless innovations and adaptations and lucky breaks that allowed your ancestors to survive and reproduce generation after generation through ice ages and volcanic eruptions and asteroid impacts and mass extinctions and every other challenge that arose. This is your heritage, your deep ancestry. And it's shared with every other living thing on Earth. You and a tree share common ancestors from billions of years ago. You and a Gorgonopsid share common ancestors from 320 million years ago. You and a chimpanzee share common ancestors from just 7 million years ago. We're all family, all connected through the simple fact of common descent from the first cells that learned to reproduce. Understanding this, really sitting with it and letting it sink in, changes everything. We're not separate from nature or above it. We're part of it, embedded in it, products of the same processes that created Gorgonopsids and dinosaurs and trilobites and bacteria. Where nature becomes conscious of itself, asking questions about its own history, marvelling at its own diversity. There's a profound peace in accepting this perspective, in releasing any sense of human exceptionalism or cosmic importance, in simply being one branch among millions on the tree of life, here for a brief moment before we too pass into the fossil record or evolutionary transformation. And from this perspective of deep time, of seeing ourselves as one small part of an enormous story, we can begin to contemplate what these ancient creatures mean to us, what their story offers us. There is a particular kind of beauty in the ancient, in things that have passed beyond living memory into deep time, in creatures and worlds so removed from our experience that we can only know them through stone and inference. This beauty is different from the beauty of living things, which we can see and touch and interact with. It's a beauty tinged with melancholy, perhaps, an awareness of loss, but also touched with wonder at the very fact that we can know anything at all about these vanished worlds. Consider the first time you saw a reconstruction of Dimetrodon, whether in a book or museum or documentary. There was probably a moment of surprise, of quote 24, followed by curiosity. That distinctive sail, those long teeth, the heavy body and sprawling limbs. It doesn't quite fit into any modern category. It's not a dinosaur, despite often being mistakenly grouped with them. It's not a modern reptile. It's its own thing, unique to its time, and there's beauty in that uniqueness. Or consider the fossil beds of South Africa, the Karoo Basin, where thousands of Permian synapsids have been discovered. Walking through that landscape today, you see scrubland and rocky outcrops, fairly barren and dry. But 260 million years ago, this was a more lush environment, home to herds of dicynodonts, packs of gorgonopsids, forests of seed ferns and conifers. The very rocks beneath your feet contain the remains of that ancient world, waiting patiently to be discovered, to tell their story. There's beauty in the patience of fossils, in the way they wait in stone for millions of years until erosion or excavation brings them to light. A Gorgonopsid skull, preserved for 255 million years, contains within its structure information about how the animal lived, what it ate, how its brain was organized, how it grew from infant to adult. All of this encoded in bone, in the precise shape and size and arrangement of structures that once surrounded living tissue. There's beauty too in the process of discovery, in the paleontologist carefully excavating a specimen, brushing away matrix grain by grain, revealing bones that haven't seen light since the Permian. In the lab work that follows, the preparation and study, the comparison with other specimens, the gradual building of understanding. In the illustrations and reconstructions that bring these creatures back to life, if only in imagination, allowing us to visualize what was once real but is now lost. The names themselves carry a certain poetry. Gorgonopsid, quote 25 Dimetrodon, quote 26 Lystrosaurus, quote 27. These names are windows into how we understand these creatures. What features struck the scientists who first studied them as most remarkable or characteristic? Behind each name is a story of discovery, of someone carefully studying a fossil and choosing words to capture its essence. There's beauty in the incompleteness of our knowledge, in the mysteries that remain. We don't know what colour Gorgonopsids were. We're not certain whether they had hair. We can infer behaviour from anatomy and modern analogues, but we'll never see them move, never hear the sounds they made, never smell the scent of a Permian forest, or feel the texture of a cynodont's fur. These unknowns are frustrating to paleontologists, but also preserving of wonder, spaces where imagination can still roam. And there's beauty in the connections, in tracing lineages across millions of years, in seeing how a pelycosaur jaw gradually transforms through theropsid intermediates into a mammalian jaw, in understanding that your own ear bones were once part of a reptilian jaw, in recognizing family resemblance across a gulf of 270 million years. The reconstructions themselves, the artistic recreations of these creatures in their environments, represent a particular kind of beauty. Artists combine scientific knowledge with creative vision to show us animals we can never photograph, landscapes that no longer exist. These reconstructions are interpretations, educated guesses, but they're also acts of resurrection, bringing the dead back to life, if only on canvas or screen. Museums full of fossils are temples to deep time, spaces where we can stand before actual bones from the Permian, where we can see with our own eyes the evidence of these ancient lives. There's something profound about looking at a Gorgonopsid skull, knowing that this specific animal lived and breathed and hunted 255 million years ago, that these teeth once bit into flesh, that these eye sockets once held living eyes that saw a Permian landscape. This is why we study paleontology, why we care about creatures so long dead they're essentially alien to us. Not just for scientific knowledge, though that's valuable, but for the beauty and wonder of it, for the expansion of imagination that comes from truly comprehending deep time, for the connection to our own deep past, for the simple fact that these ancient lives matter and deserve to be remembered. In a sense, we're the only memory these creatures have. The universe doesn't care that Gorgonopsids existed. The laws of physics don't preserve the memory of Dimetrodon's sail. Only we, through our study and curiosity and wonder, keep these ancient lives from being not just dead but forgotten. We become witnesses to the Permian, testifiers to its existence, preservers of its story. And in doing this work of remembrance, in caring about creatures dead for hundreds of millions of years, we affirm that life matters, that every organism that successfully lived and reproduced has value, that the story of Earth is worth knowing, that deep time is worth exploring. This is the beauty in the ancient, not just that these creatures existed, but that we can know they existed, can reconstruct their lives, can honour their place in the long story of life on Earth. Let that thought settle as we move forward, as we begin to draw the threads of our journey together. What can these ancient creatures, separated from us by hundreds of millions of years, teach us about life, about change, about our own place in the cosmos? The lessons are subtle, nothing so simple as moral fables, but they're there if we're willing to look, willing to sit with the implications of deep time. First, there's the lesson of impermanence. Every creature we've discussed tonight is extinct. Every ecosystem vanished. The Gorgonopsids, which dominated for 10 million years, are gone. The Dicinodonts, which survived the worst mass extinction in Earth history and thrived for tens of millions of years, are gone. The Cynodonts, our own ancestors, are gone in their original forms, transformed through evolution into creatures they wouldn't recognize. This impermanence extends to everything. No species lasts forever. No ecosystem remains unchanged. The very continents shift. The climate changes. The composition of the atmosphere varies. What's true at one moment in Earth's history becomes false at another. There are no permanent truths in biology, only temporary adaptations to current conditions for us. Living in a human culture that values permanence, that builds monuments and institutions meant to last forever, this is a challenging lesson. Nothing lasts. Not species, not civilizations, not planets, not even stars eventually. Everything changes. Everything passes. The only constant is change itself. But this isn't a nihilistic message. It's liberating. If nothing is permanent, then failure isn't final. The synapsids lost to archosaurs in the Triassic, but mammalian descendants eventually flourished when conditions changed again. Temporary setbacks are just that, temporary. The story continues. Evolution keeps experimenting. Life persists. Second, there's the lesson of resilience. Life has survived 5 major mass extinctions and countless smaller ones. The Permian Triassic extinction killed 96% of marine species, and yet life recovered, rebuilt, eventually surpassed its previous diversity. This has happened repeatedly. Catastrophes occur, sometimes caused by volcanoes, sometimes by asteroids, sometimes by shifts in ocean chemistry or atmospheric composition. Life suffers, populations crash. Species go extinct, and then life recovers. This resilience comes from diversity, from the simple fact that with millions of species some will survive almost any catastrophe. It comes from adaptation, from populations evolving to meet new conditions. It comes from time, from the patient accumulation of small changes that eventually rebuild ecosystems. Life doesn't give up. It can't give up. It simply responds to conditions generation by generation, and those responses eventually lead to recovery. For us, in an age where we're causing our own mass extinction event through habitat destruction and climate change, this is simultaneously reassuring and sobering. Reassuring because life itself will probably survive whatever we do. The planet has survived worse. Sobering because the recovery takes millions of years, because the species we're losing now, including potentially ourselves, won't be part of that recovery. Third, there's the lesson of connection. Every living thing is related, connected through common descent from the fur cells that appeared nearly 4 billion years ago. You and a Gorgonopsid share ancestors. You and a tree share ancestors. This isn't poetic. It's literal biological fact, demonstrated through genetics and anatomy and the fossil record. This connection should fundamentally change how we see the world. Other species aren't resources for us to exploit or obstacles to our expansion. They're family, distant cousins many millions of times removed, but family nonetheless. The ecosystems we're disrupting aren't separate from us, but the very fabric of relationships that sustains all life, including ours. Understanding deep time and our place in it should generate humility. We've existed for 300,000 years, a geological instant. We've had civilization for 5,000 years, a fraction of an instant. We don't know how long we'll persist. The average mammalian species lasts 1 to 2 million years. We might be here for another million years, or we might be gone in a few thousand, victims of our own success and environmental degradation. The Permian creatures teach us that dominance is temporary. The Gorgonopsids were apex predators until they weren't. The Dicinodonts were the dominant herbivores until mass extinction removed most species. Nothing is guaranteed. Success in one era doesn't protect you from change conditions in the next. But they also teach us that lineages can persist through change if they remain adaptable. The Cynodont lineage survived the Permian Triassic extinction by staying small, staying flexible, being able to survive in marginal habitats when preferred environments became uninhabitable. When conditions improved, they radiated and diversified again. Adaptability, not specialization, is the key to long-term survival. Finally, there's the lesson of perspective. When you're troubled by daily concerns, by politics or career or relationships, it can help to remember that you're a member of a species that has existed for 300,000 years, part of a lineage that extends back 320 million years to the first synapsids, inheritor of nearly 4 billion years of evolutionary history. Whatever you're worried about, whatever seems crucial in the moment, becomes vanishingly small against the backdrop of deep time. This isn't to minimize real problems or suggest nothing matters. It's to say that context matters, that stepping back and seeing the larger picture can provide relief from immediate anxiety, can help us distinguish what truly matters from what seems urgent but ultimately isn't. These lessons aren't answers. They don't tell us how to live or what to do. But they provide context, framework, a longer view that can inform how we approach our brief time on this planet. We're part of something much larger and older than ourselves, and there's peace in that recognition. And so we come to understand, slowly, what these ancient creatures can give us. Not just knowledge about the past, but perspective on the present, context for our own existence, connection to the long story of life on Earth. Standing at the end of our journey through 300 million years of Earth history, we can see a continuum, an unbroken chain linking the Carboniferous giants to this present moment. The creatures that ruled before dinosaurs aren't separate from us, aren't irrelevant to our current world. They're the foundation upon which everything that came after was built, including us. Consider the air you're breathing right now. The oxygen in it has cycled through Earth's atmosphere countless times over billions of years. Some of those same oxygen molecules might have been breathed by a Permian Gorgonopsid, might have fueled its metabolism, powered its muscles during a hunt. The atoms that make up your body have existed since the formation of Earth, maybe since before Earth, forged in stellar furnaces billions of years ago. They've been part of countless organisms over geological time, cycling through the biosphere, from plant to herbivore to carnivore to decomposer, and back to soil and plant again. The carbon in your bones might have been part of a carboniferous tree, compressed into coal, eventually released through volcanic activity or human mining and burning, taken up by plants, eaten by animals, eventually incorporated into your own tissues. You're literally made of recycled dinosaurs and gorgonopsids and trilobites and algae, all the way back to the first cells. This material continuity is matched by evolutionary continuity. The genetic code you carry is the same basic code that existed in the first cells, modified and elaborated over billions of years, but still recognizably the same system. Your cells work fundamentally the same way as bacterial cells, using the same basic chemical reactions to generate energy, to synthesize proteins, to replicate DNA. The structures we've discussed, the synapsid skull opening, the differentiated teeth, the diaphragm, the three-boned mammalian ear, these didn't appear de novo. They evolved gradually through countless small modifications over millions of years, from the pelycosaurs through the therapsids to the cynodonts to early mammals to modern mammals. Each generation was slightly different from the one before, but the changes were small enough that every organism was reproductively compatible with its parent's generation. Yet accumulate these tiny changes over millions of generations and you get transformation, from pelycosaur to mammal, from sprawling quadruped to erect walker, from simple teeth to complex dental battery. This is the continuum of evolution. Small changes accumulating over vast time, leading to outcomes that would seem impossible if you only looked at a single generation, but become inevitable when you understand the process playing out over millions of years. The ecosystems we inhabit today are descendants of Permian and Triassic ecosystems. The basic structure hasn't changed. Plants capturing solar energy, herbivores converting plant matter to animal protein, carnivores regulating herbivore populations, decomposers recycling nutrients. The specific species have changed, the particular adaptations are different, but the fundamental relationships, the energy flows, the cycles of nutrients, these are the same as they were 300 million years ago. When you watch a nature documentary showing lions hunting zebra in Africa, you're watching a reenactment of gorgonopsids hunting dicynodonts in the Permian, the same basic predator-prey dynamic playing out with different actors. When you see a herd of elephants browsing on trees, you're seeing the modern equivalent of Dicinodont herds grazing Permian landscapes. The details differ, but the patterns persist. This continuity extends to behaviour as well. Social structures in modern mammals, pack hunting in wolves or complex hierarchies in primates, likely have roots in ancient synapsid behaviours. We can't know exactly how Gorgonopsids behaved, but the capacity for complex social interaction probably evolved early in synapsid lineages, was present in cynodonts, and has been maintained and elaborated in mammals ever since. Even human culture, our unique ability to accumulate and transmit information across generations, to build on previous knowledge, to imagine and create. These capacities have roots in our mammalian and synapsid heritage. The brain structures that support culture, particularly the neocortex, evolved gradually in mammalian lineages, building on older structures inherited from reptilian ancestors, which in turn built on structures inherited from fish and even more primitive ancestors. We're not separate from this deep history. We're its latest expression, its current manifestation, carrying forward everything that came before us, while adding our own unique elaborations. When humans go extinct, as eventually we must, we'll leave our own mark on this continuum, our own contribution to the ongoing story of life on Earth. Some of our descendants, whether biological descendants or descendants of other species that we've influenced, will carry forward aspects of our legacy, just as we carry forward the legacy of Gorgonopsids and cynodonts and early mammals. This perspective can be vertiginous, overwhelming even. To see yourself as one small link in a chain stretching back billions of years and potentially forward billions more. To understand that you're both unique and utterly typical, both special and completely ordinary in the context of deep time. This requires a shift in thinking, a willingness to see yourself as part of a process, rather than as a separate observer of that process. But this shift, once made, brings peace. You're not alone, not separate. Not an isolated consciousness in an indifferent universe. You're part of the great continuum of life, connected to everything that has lived and everything that will live, a temporary manifestation of a process that's been ongoing for nearly 4 billion years and shows no signs of stopping. The Gorgonopsids and Dicinodonts and cynodonts are part of you. Their innovations live in your body, their adaptations enable your existence. And you're part of them, a continuation of their lineages, evidence that they succeeded, that their experiments worked, that the chain wasn't broken. From the Carboniferous to now, from giant dragonflies and sprawling pelycosaurs to Gorgonopsids and cynodonts, to dinosaurs and early mammals to primates and humans, it's all one story, one unbroken narrative of life adapting and changing and persisting. We're living the next chapter of that story, and whatever comes after us will be the chapter after that. And so we find ourselves at the threshold of rest, having travelled together through 300 million years, ready to settle into sleep with new perspective on our ancient world. As we near the end of our journey, as your breathing has hopefully slowed and your body has settled into stillness, let's return one final time to those ancient landscapes, those Permian forests and Triassic plains, and find in them not fear or anxiety, but peace and comfort, and a kind of quiet wonder at the simple fact of existence across such vast spans of time. Imagine, if you will, a late Permian evening, 255 million years ago, in what is now South Africa. The sun is setting, casting long shadows through a forest of seed ferns and early conifers. The air is warm, humid, filled with the chirping of early insects and the calls of small vertebrates seeking shelter for the night. In the undergrowth, small Dicinodonts are returning to their burrows, family groups settling in together for safety during the dark hours. Somewhere in the forest, a Gorgonopsid has made a kill and fed to satiation. It lies now in the shelter of fallen logs, resting, digesting, no longer hunting because its immediate needs are met. Its breathing is slow and steady. If it could feel something like contentment, this would be that moment, full belly, safe place to rest, another day survived. In a river nearby, a large temnospondyle floats just beneath the surface, motionless, conserving energy in that particularly amphibian way. Neither fully awake nor fully asleep. Small fish move around it, too small to be worth the energy of catching. The water is cool and oxygen-rich, flowing steadily toward a distant sea. Higher in the canopy, a small early archosaur, barely the size of a modern lizard, has found a safe branch for the night. It's eaten its fill of insects through the long day, and now it simply rests, clinging to bark with its claws, eyes closed, body temperature dropping to match the cooling air. Entering that reptilian state between sleep and torpor. And everywhere, in the soil and water and air, countless smaller creatures are doing the same, eating or being eaten, resting or hunting, breeding or dying, living out their brief lives as best they can in the conditions they find themselves in. This is an ecosystem at work, billions of individual lives intersecting, competing, cooperating, forming the complex web of relationships that sustains them all. There is peace in this scene. Not the absence of predation or death, not some sanitized Disney version where nothing dies. Real peace, the peace of a functioning ecosystem, of animals well adapted to their environments, of life doing what life does, generation after generation, without anxiety about the future or regret about the past. The Gorgonopsid doesn't worry that its species will go extinct in 7 million years. The Dicynodonts don't fear the mass extinction that will devastate their lineages. They simply live, moment to moment, responding to hunger and safety and reproduction and threat as these arise. This is the peace we can take from deep time, the understanding that life continues regardless of individual anxieties, that the process is larger than any individual participant, that there's a kind of rightness to simply being alive and responding to conditions as they arise, without trying to control outcomes too far in the future. In the vast sweep of geological time, human worries appear as ephemeral as they truly are. The anxieties that keep you awake at night, the concerns about status and success and what others think of you, these matter in the context of human society, but they vanish to nothing against the backdrop of 300 million years of Earth's history. This isn't to say your concerns don't matter at all, just that their importance is contextual, limited, something that can be set aside when perspective is needed. The Gorgonopsids and Dicynodonts teach us to live in the moment, not because they were wise or enlightened, but simply because they had no choice. They couldn't plan for millions of years in the future, couldn't worry about their species' ultimate fate. They could only respond to immediate conditions, hunger, threat, opportunity for reproduction. And in doing so, in living moment to moment and generation to generation, they succeeded for tens of millions of years. There's a lesson there for creatures like us, blessed and cursed with consciousness and foresight. Yes, we can plan and should think about consequences and futures. But we can also remember that ultimately we have only this moment, this breath, this heartbeat. The future will come regardless of our anxiety about it. The past is fixed and cannot be changed. All we have is now, and the ancient creatures, in their simple, moment-to-moment existence, understood this truth better than we often do. As your mind drifts towards sleep, let go of future worries and past regrets. Be like the resting Gorgonopsid, satisfied with this moment, requiring nothing more than to be alive, to breathe, to rest. Be like the floating temnospondyle, conserving energy, moving with the current, at peace with its place in the world. Be like the small archosaur on its branch, safe in its spot, content with simplicity. The ancient world asks nothing of you. It existed before you and will exist in the fossil record long after you're gone. It simply is, was, a fact of deep time, and in its patient existence through hundreds of millions of years, It offers us permission to rest, to let go, to accept our small place in an enormous story and find peace in that acceptance rather than anxiety. Sleep well, knowing you're part of something vast and old and ongoing, that you carry within you the legacy of creatures that dominated Earth for millions of years, and that the same processes that created Gorgonopsids and Cynodonts created you, that you're one expression among billions of the simple, remarkable fact of life on this particular planet, in this particular corner of the universe. The Permian forests are dark now, as is your room, wherever you are. The ancient creatures are settling into their own kind of rest, and you can do the same, releasing into sleep, letting the story of deep time carry you gently into dreams of ancient worlds and distant times, of creatures both strange and familiar, of the long, patient unfolding of life across geological ages. Rest now. Let the Permian darkness be peaceful, not frightening. Let deep time be comforting, not overwhelming. You're exactly where you should be, when you should be there, doing what all living creatures do, existing, breathing, resting, being alive for this brief moment before you too pass into the great continuum of life on Earth. Thank you for staying with me through this long journey into deep time. We've travelled together for 2.5 hours now, moving slowly through 300 million years of Earth's history, from the Carboniferous giants, through the Permian rulers to the Triassic survivors, and the dawn of the Dinosaur age. It's been a long voyage, and I'm grateful you chose to take it with me. From the massive dragonflies of the Carboniferous to the sail-backed Dimetrodon of the early Permian, from the powerful Gorgonopsids to the adaptable Dicynodonts, from the vast temnospondyle amphibians to the small cynodonts that would eventually lead to mammals, we've met the creatures that ruled Earth before dinosaurs. We've watched ecosystems form and function, and ultimately collapse in the worst mass extinction in Earth's history. We've seen recovery and renewal in the Triassic. We've traced the origins of our own lineage back through cynodonts and therapsids to those first synapsids in the late Carboniferous. What have we learned? Perhaps the answer, as honestly as I can give it, is that these ancient creatures teach us about impermanence and resilience, about connection and perspective, about the vast sweep of time and our small but meaningful place within it. They show us that dominance is temporary, that lineages persist through adaptation rather than resistance to change, that life always finds a way even after the most catastrophic extinctions. Most importantly, they connect us to our own deep past, showing us that we're not separate from nature but part of it, carrying within our bodies and behaviours the legacy of creatures that lived hundreds of millions of years ago. Every breath you take, every beat of your heart, every tooth in your jaw, these are gifts from the Permian and Triassic, adaptations refined over millions of years and passed down to you through an unbroken chain of successful reproduction. If you enjoyed this slow drift through deep time, a like and subscribe would mean the world to me. These documentaries take significant research and care to create, and your support helps me continue making them. Please feel free to leave a comment about what you found most fascinating or surprising in tonight's journey. And to those already subscribed, to those who've been here before and chose to return, thank you. Your ongoing presence in this community of curious, contemplative minds is what makes this work meaningful. Wherever you are in the world right now, whatever space you've carved out for this quiet ending to your day, I hope you're comfortable. I hope your breathing has slowed and deepened. I hope your thoughts have quieted, your body has relaxed, your jaw is unclenched, your shoulders have dropped away from your ears. I hope the worries of the day have faded to background noise, manageable and distant. I hope you feel heavy and warm, settled and safe, ready for sleep. Look up at the stars tonight if you can, or imagine them if you can't. Those same stars, or their ancestors, shone down on the Permian landscapes we've been exploring. Photons from distant suns illuminated the Gorgonopsids' hunts, warmed the backs of basking Dicynodonts, glinted off the eyes of predatory temnospondyls. The universe that held the Permian world is the same universe that holds us now. We're made of the same elements, governed by the same physical laws, part of the same ongoing story of matter and energy and life. All those ancient creatures, all those vanished ecosystems, all that lost time, they're not really gone. They're preserved in rock, yes, in the fossils we've discussed, but they're also preserved in us, in the lineages that survived and adapted and eventually gave rise to mammals and primates and humans. The Gorgonopsids live on in our differentiated teeth. The cynodonts live on in our diaphragm-powered breathing. The earliest synapsids live on in our skull structure and our basic body plan. Nothing is ever truly lost. It's all transformed, recycled, passed forward through time in new configurations, new expressions of the same basic patterns. You're a transformation of Gorgonopsid, of cynodont, of early mammal, of primate ancestor. All of that history is encoded in your genes, expressed in your anatomy, active in your physiology. Your deep time made conscious, the Permian and Triassic walking and breathing and thinking about their own past. There's a kind of peace in this acceptance, in understanding that you're both utterly unique and completely typical, both unprecedented and yet part of ancient patterns, both individual and deeply connected to everything that has lived. You're a moment in the great continuum, brief but real, meaningful but not essential, here for a time and then part of what comes next. Sleep well. Dream of ancient forests and strange creatures, of sail-backed predators and tusked herbivores, of flying insects the size of birds and amphibians as large as crocodiles. Dream of a world both alien and familiar, separated from us by incomprehensible time, yet connected through the simple fact of shared inheritance, of common descent from the first cells that learn to reproduce. Dream of Gorgonopsids resting after the hunt, of dicynodonts safe in their burrows, of cynodonts breathing with their new diaphragms, of all the small innovations and adaptations that eventually led to you. Dream of deep time not as something to fear or be overwhelmed by, but as a comfort, a reminder that life continues, that the story doesn't end, that what came before us succeeded for long enough to give rise to us, and what comes after us will be their own success story, built on the foundations we leave behind. The Permian night is dark and quiet and peaceful. The ancient creatures are at rest. The forests sway gently in warm breezes. Rivers flow toward distant seas. Stars wheel overhead. Indifferent and eternal, and somewhere in that vanished world your ancestors, many millions of generations removed, are living their lives, moment to moment, doing what they need to survive. Without knowledge of you, but nevertheless essential to your existence. Thank you for being here. Thank you for caring about these ancient lives. Thank you for your curiosity and your willingness to sit with deep time and find in it not anxiety but wonder. Good night. Sleep deeply. Rest well. And when you wake, carry with you the knowledge that you're part of something vast and old and ongoing, that you contain within you the legacy of the creatures that ruled before dinosaurs, that you're a small but real part of the great story of life on Earth. May your dreams be peaceful and your sleep be deep. Good night.